Hello and welcome to today's webinar. It is the first tutorial in our series about distance protection. My name is Jose Malagon and I'm a technical consultant for process bus and power system stability. Today, I'm the moderator and I have the honor to guide you through this webinar. So, distance protection, what is it? How does it work? Why do we use it? Where do we use it? A lot of questions that I'm sure will be answered in today's session. The expert presenting the topics today is my dear colleague and master, Mr. Gustav Steinberg. I'm sure he is already well known as, or I guess I can say, as the expert for line protection. Of course, you will have the chance to ask questions. You can type your questions in the questions field or in the chat during the whole webinar. And I will be your voice and read the questions to our expert. We will have 2 short breaks. Q&A sessions are planned before the breaks and at the end of the session. All the questions that we won't answer today will be answered after the webinar in a written format. So please don't hold back and ask everything you want to know about the distance protection. Now I'm happy to hand over to Gustav, and he will start with the first part of this interesting training. Welcome, Gustav.
Thank you very much, Jose, and welcome from my side to all of you. I hope I'm not a new face to everybody, but to those that don't know me, I hope that you will remember me after this presentation. Distance protection has been a hobby of mine for a long time, and I was thinking how to explain it in a presentation in a relatively short time. And I said, let's do it with some questions and answers. And I think what is the typical question you will have would be what is a distance protection? For some of you, that would be an easy answer, and you would say, I know, but maybe it's a good time to rethink it. What you know, probably if you know anything about distance protection, it's fairly complicated. So the question then is, why would we use something that is so complicated? And that I will try to explain the real big advantage of having a distance protection. And then finally, a little bit, how does it work? Because if we're going to use it, we need to also know how it works. So at that point, let me go straight into the question, what is a distance protection? If we look at this little diagram here, you can see it shows a little bit the history, and sometimes I worry because I'm not so young anymore that my life covers almost half of this. Electricity has not been around for so long if we think about humanity, but in this diagram you see in about 1910, protection was first used by Siemens, and the distance protection was part of this from a very early time, probably almost completely on the left-hand side in that diagram. Now, around about 1920, we have in the 1920s, the first reference to distance protection. So it has been with us a long time, so it shows that it is an important function, and otherwise it would not have been there at that early stage. So if we look at this diagram now, what is it? The distance protection is a protection that, as you can see here, measures current and voltage. And then probably at the lower diagram, you see there are some zones that are applied, and you are trying to establish is a fault in a certain area or not. And this is going to be very important for a selective protection, and that is the ultimate purpose of protection, to achieve selectivity. So basically, distance protection is going to measure current and voltage. It's going to use, as you see at the top, an impedance principle to establish, to localize the fault location. That's why sometimes impedance protection, distance to fault, localize the fault, identify which area it is in, and then make a trip decision. And very important in this trip grading for the selectivity is also time. So you can see the time criteria, we have certain zones with time delays. That in a nutshell is what distance protection is. From the early days, we saw earlier on the diagram, I said in the early 1920s, we did not have any electronics as such, transistors and that type. At that time, it was electromechanical. And you see a little diagram here showing how roughly in a schematic way a distance protection was constructed. You have seen there's 2 windings, a current and a voltage winding. As you see, the 2 measurements we used previously for the impedance protection. And the current would be the operating criteria, so pulling down to try and close the trip contact, and the voltage is a restraint criteria preventing the pivot of this axis over here. So voltage, restraint, current, operate, and a little spring at the top, you see the control spring, would be kind of setting a characteristic. And like that, you can construct a very, very primitive or very simple distance protection. And if one uses very quality electromechanical equipment, you can get a very high quality protection. If we now apply that to try and get a selective tripping, we have to come to the other issue we see at the bottom left-hand side, the zones. So we classify for the distance protection, we have to apply a characteristic. And in the old days, electromechanical, you would have to construct two characteristics or change a method of operation to have an element, a measuring element, and the measuring element would have a boundary, and the boundary would be a zone. We'll see that a little bit later on in the other descriptions as well. So ultimately, you identify a zone, and the zone would operate for faults in a certain area, and another zone in a different area, and that together with time grading is going to achieve the selectivity. So ultimately, you can see here, the purpose is to trip on the F1 with this relay and not to trip on the F2. That is going to be the ultimate objective that the distance protection will achieve. And we'll see how that is done later on. The characteristic we just saw, the electromechanical one, this very simple one I showed here, ends up with a circular characteristic. And this is interesting. We'll see the circular characteristic later on as well. And often in literature, you see these diagrams. And we'll also look at one particular circular characteristic, the MO, a little bit later on. And that is the result of this method here. Why is it such a simple characteristic? Because obviously, if we're going to apply this method here, it is a simple magnitude comparison over here, because the basically going through the iron here, you're going to get an average response, and that is going to then rectify it, and you will not have any phase information. You see the two equations on the left-hand side. The top is the Z, the complex impedance, as we'll see later on in numerical relays. And at the bottom is the magnitude. You simply, like an electromechanical relay, would have a magnitude response and only give you a circle. So you would not know where in the circle the impedance is, but you know it's somewhere inside the circle or outside. It is not directional. This is obviously a big risk constraint, because if we don't know if the fault is forward or reverse, then in terms of selectivity, we have a big problem. All right. So a directional characteristic will be added, and this, I show this here as a highlight, because even today, in the most modern distance protection relays in microprocessor, we do still apply this principle of doing the directionality as a separate measurement to the reach. The reach measurement, which is inside the circle or outside, is done together with a separate direction measurement. The direction measurement has got other prerequisites or other demands that it has different to a reach measurement. That's why it is done in two measurements, and you combine them to get the ultimate characteristic here, as is shown as a graphic example here, to make the circular characteristic directional. All right, now we come, after clearing up what the what is, a distance protection is, why do we use it? As we saw now, it is not the simplest technique, so we must identify why would we do something like that? And I have a couple of diagrams to show that, because if you look at this situation here, the classic selectivity, tripping on the internal fault and not tripping on the external fault, is the requirement. And the distance protection can achieve this. And I'll show later on that other techniques like an overcurrent cannot achieve this. That is why we're using a distance protection. This example here, you can see the top and bottom, the two circuit diagrams represent a symbolic, are identical, except for the situation that you have that the green arrow shows you that at the top left-hand side, you have the breaker closed, and at the bottom left-hand side, the breaker is open. So it is the same system conditions, except for one switching operation, which can happen at any time. And in terms of a protection, if you now look at where I localized the protection relay there, the distance relay in blue, the blocks you can see down at the bottom here, and the same in the other diagram. For that protection, for the external fault at the bottom here, this F2, you can see that the current is 12 kiloamps about, because it's all flowing in the bottom feeder, the top path is open. And in the other diagram on the top here, you can see the breaker is closed and is on the internal fault only 10 kiloamps flat. So an overcurrent protection, if that 21, this distance relay, were an overcurrent relay, it would not work correctly, because it sees 12 kiloamps on the external fault and only 10 kiloamps on the internal fault. So Knowing overcurrent protection, it will not achieve a selectivity over there. A distance protection will achieve that, and we'll try and show that in a couple of diagrams now. For this ultimate, well, not say ultimate, for this distance protection selectivity, all you need is two zones. And these two zones are classified as normally we call it the zone 1, an underreaching zone, and you have an overreaching zone, the zone 2. And they have two very clear requirements. The underreaching zone, zone 1, requires here a safety margin. And the safety margin is, as we'll see later on, to allow for tolerances. So it may never pick up on an external fault. This is so you need a safety margin to see the fault is on a remote bus bar or further away. It may not pick up. And the other zone, the zone 2, is our overreaching zone. It must cover the complete line. So it has a security margin here to make sure that it will always see internal faults. It will not fail to pick up on an internal fault. This is the two basic definitions of a zone 1 and the zone 2 as we are going to use it in this example. All right, we're going to go through a simple series of slides now to explain how the distance protection is going to get a selective fault clearance of this fault over here. We have the line at the top, AB, and that's the faulted line, and the bottom line is shown protected in the same manner, and it will also respond. Now, because we saw the directionality is given on the bottom feeder, there will be no pickup on the right-hand side. There will only be a zone 2 pickup on the left-hand side, because obviously the zone 2 is overreaching and would see beyond the line and would pick up on that fault B. Is that a problem? We'll see, not really, because initially what we will have picked up is the zone 2 at the bottom, as we just explained, and on the top, the zone 1, obviously on the right-hand side, and on the left-hand side at A, we will have the zone 2 pickup. The pickup takes a certain time. I showed it at the top, around about 20 milliseconds is roughly the pickup time. So all these three relays will pick up in these 20 milliseconds. With the time grading, only the zone 1 is going to issue a trip now. So in this stage, now after that zone 1 pickup will result in a trip. That trip will go to the breaker. The breaker has a certain response time. I showed it here, about 3 cycles. That takes at 50 hertz. So at 80 milliseconds, the breaker at B is open. First step, so good. And you can see where this is going, because when this breaker at B is open, the zone 2 over here will no longer be seeing the fault. Now you go into the reset time. The zone 2 is going to have a drop-off time, again, approximately 20 milliseconds. Zone 2 at the bottom will be dropped off. And then the zone 2 timer at the top, it will be running. We'll run time out. Typical time grading is around about 250, 300 milliseconds. And then here after timeout, this zone 2 at A is going to trip. And we will see with the reset at the bottom and the zone 2 trip at the top, the fault is cleared selectively. And that is essentially how a selective distance protection in its most basic form will work and can achieve this. And there is, if you change the in-feed conditions, there is no other protection function that can do this. You cannot depend on differential protection because it's communication related. If we add you don't have any communication here. You cannot do it with overcurrent protection or any other protection. So without communication, for selectivity, you need distance protection. And just to summarize again, the important aspect, the zone 1, remember, needs the safety margin. It must underreach. It may never pick up on the external fault. And the zone 2 needs a security margin. It must cover the feeder. That's the fundamental requirement of those two zones. All right. Having now looked at what and why, we now come to the third question, which is how. Okay, and there we can spend a lot of time, but I obviously choose a few examples for the how. And the first one, again, going maybe to the electromechanical comparator, but that was replaced by electronics a little bit later. And you can see here now, instead of the electromechanical operator, we have now an electronic comparator here, but in principle, it is still operating in a very similar manner, this comparator. And it uses the principle of converting the measured current to a voltage via a replica impedance. And this is a very basic method of a distance protection. This replica impedance corresponds to the zone setting. So it is an impedance, and if you convert it now to primary and secondary, we'll see later on, the importance of understanding what is a secondary impedance and a primary impedance. Obviously, over here, we are working with secondary components, secondary current, and secondary voltage. So we are here in the secondary world, but that can be converted to primary. So if we say this impedance here, this replica models the primary zone boundary, then we can imagine if a fault were at the zone boundary, and this is going to be interesting, then based on this model, the voltage you measure here would be equal to the voltage you get across the replica impedance, because this here is modeling what is happening on the primary side. If the fault is at the zone boundary, which corresponds to the Z replica impedance, by Kirchhoff's voltage loop, the voltage here created on the secondary side must equal the measured voltage here, because it is a model of what's happening on the primary side over here. And correspondingly, if the fault is closer, what will happen is that this voltage here will be larger. The current quantity is bigger. It's the operate quantity, and the voltage will be smaller. And the comparator will say inside and give you the trip. And very interesting, it's a circle again. This is obviously doing exactly the same as that electromechanical bridge effort did over there, and the characteristic is a circle. So having come back to the circle, even with this electronic comparator here, I decided let's maybe look at the most famous circle we have in protection, and that is the Mohs circle. Now you can see this interesting thing here. The Mohs circle is copied from the manual. This diagram, you may have seen it before, is offset. It's including the origin over here, and this will explain this a little bit later. This is a memory voltage polarized or quadrature polarized Mohs circle. This polarization gives it this directionality. Now, initially you can think, but if it's including the origin is non-directional, we see later on that this Mohs circle is dynamic. It shifts depending on the fault location. So how does one create such a circle that is now not the circle we saw previously around the origin, but a shifted circle as such? And how does one measure this with a fairly simple function? Because this was already also implemented with electromechanical relays. This can be implemented with electromechanical, and analog does not need a numerical device and was used very extensively early on. What you see now here is this Mohs circle, now not offset. Basically, it is through the origin. This is the classic Mohs circle, not offset. It's a self-polarized Mohs circle, we can say. And how does one do this? Okay, how does a distant protection do this? And this is simply, again, a comparison of voltage signals. You can see there are 3 voltage signals that create the circle, and they create a triangle over here. And these 3 sides of this triangle are the interesting one. The most important one is the diameter here. You can see the diameter of the circle is very, very important. And that is our I times Z replica. As we saw earlier on, that current flowing through the replica impedance is this blue one here. This would be our operate quantity, so to speak. The other quantity you see now here is the measured voltage. Okay, and it's interesting. Before, we were just making a balance between those 2, blue and white, and that was a non-offset circle. But now we do something creative. We create this orange phasor here, and this orange phasor, interesting, is this difference. It's this IZ, the blue phasor minus the measured voltage. All right, and this gets this. And now we use an interesting technique, is that you know from your trigonometry in school, if you take a circle and you make a diameter, then any triangle with a point over here on the circumference of the circle will have a 90-degree angle over here. This is a definition. You can move this to any point here, this triangle point here. As long as it's on the circle, the angle will be exactly 90 degrees. And that we can use. So the definition of this triangle is the fundamental definition of the Mohs circle. You can see this here, the triangle now is defining the Mohs circle. And this boundary condition here, 90 degrees. So interesting to see how will the characteristic now work. It's going to just simply check this 90 degrees over here, because you can see if the fault is inside, the angle is larger than 90 degrees, and if the angle is outside, the fault is outside, the angle will be smaller than 90 degrees. And this is very advantageous to us because checking an angle is much simpler than it seems. Checking an angle is simply checking time. At 90 degrees, at 50 hertz, 90 degrees equals 5 milliseconds. right? And so what you do is you take your waveforms, which are the voltage waveforms, we are on those phasors, and we basically turn them into a square wave by just running through a comparator like that. Then you take the two square wave of which you want to compare the angle, and you overlap them through another comparator, and you get basically the interval of overlap over here. And the interval of overlap is the definition of the angle. Over here we have an angle which is larger than 90 degrees because the overlap is larger than 5 milliseconds. So that's a very simple way of measuring an angle. And you can run that here through this diagram over here, all with discrete electronic components. And this is how the Mohs circle was done in older relays. In numerical relays, it's done obviously with microprocessors more effectively, but in essence, it's the same technique that you are doing. Just taking the voltage and this IZ, take the difference over here. You see in that IZ, you rectify the IZ and you compare it to the measured voltage. That's the angles. Then you do the angle comparison here. And then if the angle is larger than 90 degrees, basically the time will be bigger than 5 milliseconds. The angle is smaller than 90 degrees, it will be smaller than 5 milliseconds. So if the time 5 milliseconds expires, then it was inside, it had a large angle. If the time is 4 milliseconds, for example, it's extra, you won't get a trip. So if the time, only when the 5 milliseconds expires, you are inside the characteristic. Very simple way of doing that. The problem is, this Mohs circle is running through the origin. So this is where the relay is located. So if you have the forward or reverse fault, it is on the boundary. And this is not good because the fault right in front of the relay is right on the boundary and you don't have a dependable operation. That's why the Mohs circle is offset. Remember the situation of adding a directional characteristic after doing the reach characteristic. And it's essentially the same thing here, only in the Mohs, it's all mixed up together and it is one combined measurement now. So to add the directionality, the Mohs circle is offset. Okay, and the offset is done by adding a polarizing voltage to the measured voltage. So remember we had the measured voltage, which was from the blue to this origin over here, and we just shift this measured voltage by adding to it a certain portion of memory voltage or healthy phase voltage, a polarizing quantity to that. Okay, and I'll see another example here. You can see in this example that there is the memory voltage. The memory voltage was the fault voltage before the fault, a healthy voltage before the fault occurred. It should essentially have pretty much the same angle as the measured voltage. You can see the little yellow voltage here, the measured voltage during the fault. During the fault, the voltage collapses to a much smaller value. But it's important, the polarizing voltage should have essentially the same angle as the faulted voltage. We'll see that later on as well, that is in a conventional electrical system, that will be the case. Now we don't add the full memory voltage because that would, imagine if you did that, you would have a really huge circle here because it would shift the circle here, not only to that point, but down here. We add a percentage. We'll see that as a setting even just now. On the left-hand side, it's zoomed in to just show you the expansion, the measured voltage, and then the expanded polarizing voltage is a measured voltage plus the polarizing voltage, Vmem, memory voltage in this example. All right, just to clear it up for you, a photograph or screenshot from the manual again to just take away your worries that the Mohs circle is not going to be properly selective at the near faults. If the fault is forward, the expansion is as you see, but if the fault here is reverse at this point, then the Mohs circle expansion is there, because obviously if the fault forward reverse here, the current reverses direction. Remember we have the IZ, through a replica impedance that will change its direction, and that means that the expansion is then not during forward faults, you will expand. During reverse faults, it's the opposite direction. You get a shrinkage due to the polarization. So you get a very dependable directional criteria with the polarized Mohs circle. And in order to achieve this polarization here, you can see there are settings. It's now, we're starting to see here some settings from the relay. The screenshot again. In the graphics, if you look at the graphics in Dixie, you'll see the self-polarized Mohs shown there, but you won't see the polarized. The Mohs circle is always shown in this manner, as you see in the diagram here. You never really see a graphic of the expanded Mohs, but really one has to know that in reality, during the fault, the Mohs circle is expanded. And the amount of polarizing, you can see here, we've set here in this example, it's the default setting 15%. You can see it's memory voltage, and we are dual polarized. We're polarizing with memory voltage and healthy phase cross polarization. We'll see a little bit more about what healthy phases are later on in this presentation. All right, enough of the Mohs circle, but the Mohs circle is not really a characteristic we recommend. It is just a historical, because remember, we're looking at what distance protection is. That's what we're on about. And so moving forward now to numerical relays. Numerical relays are now, we saw the electromechanical, we saw the Mohs circle created with maybe an analog electronic environment. Now with numerical relays, we have a different approach. In the numerical relays, you will take the signals. We see here our signal shown symbolically here as this sine wave, and we'll sample it, sampling it at certain intervals, and then digitize it. It goes into a digital, so for the microprocessor to compute it, it is digitalized. So you have sampled every individual sample there. And then that is not really that helpful yet, because now you can work with and sampled value algorithms, normally not preferred, because you prefer to run this through a filter, because the filter will take away some disturbances and so on, and kind of smooth out and reduce your error susceptibility. And then one combines this filtering technique immediately also with extracting what we need, and that is this phasor. So you basically run it through an orthogonal filter. I don't want to do filter theory. There are different techniques of doing this, but the advantage of the orthogonal filter technique is that you get directly out two components. The two components are the example here, real imaginary component, the quadrature components of the phasor. So you can define, extract from an analog signal here through this quadrature orthogonal filters here, a phasor. And that is really a big thing, because remember right at the beginning we had the diagram here, or the equation, and we said we could not make this complex division. Now we can, because now we have the complex phasor, voltage current with angle and magnitude, or shown here in its quadrature components. There's just the filter characteristics here. I think we don't need to discuss that much. The signal has got some distortion, this filtering. One has to be careful how one constructs these filters, because you can see there's a current waveform. Current waveform at default has a DC offset, and you can see in the purple waveform there is some filters, need some transients, they swing in, they don't come to the best result immediately, and one optimizes. It's a science on its own to optimize filtering characteristics. But the advantage really is, if we do this with a microprocessor relay, we can, at the end, with this result, essentially do almost anything. And you can see here, we come to a really complex equation, but it's shown here symbolically because it is now an equation we can generally use. And at the bottom, you see the diagram is derived from. It is a line or protected object, normally an overhead line. You can see we've taken a fault location in the line. The fault is at the location M along the line. So M is somewhere between 0 and 1 if the fault is on the line, 0 if the fault is right in front of the relay, 1 if it's at the end of the line, at 0.5 in the middle, and so on. So M is indication. If M is smaller than 1, we are inside, and if M is larger than 1, the fault is beyond the extent of the relay. We assume here the directionality, we do not go to negative M's for reverse faults, because that is a separate issue. The directionality we can, for distance protection, assume it's always going to work, that we can set a zone, say it will be looking only in the forward direction. The top here is then the Kirchhoff voltage loop equation created with the bottom, and it applies to any fault. But remember, you'll always have the relay location where the V loop is measured over there. And from there, the relay will measure the current, the I loop. It will flow outward towards the fault, through the fault location, and then back and come back as a return current. And we must consider both paths, the outward path, MZL, and the return path, Z line return. For a face-to-face fault, it's both times the line impedance. For a face-to-ground fault, it's a line, and the ZE. And we have to, obviously, the ground fault will have a different measuring technique to cover for the ZE, which the face-to-face fault is a ZL and ZL. All right, that will come back to this equation later on. It's basically the fundamental or starting point to define how your distance relay in modern terms is going to work. If we, for example, solve this M over here, then we would know exactly where the fault location is. essentially, but the M would imply that the fault is on the line. Okay, so we would have to measure the R fault separately. So once you have extracted M is the location, assuming the fault is on the line. It is just a percentage, remember, and we'd have to convert that back to a location in a characteristic. So that's the interesting thing. You would set a characteristic. So calculating M here is indication inside, outside, but it would not directly be able to give you a cross over here, because remember, this cross has got an X and an R. So you have to basically, to plot it into a characteristic, go back to an X and an R. But that is something that we have to just understand in the method of setting the relay. The setting at the relay of the distance relay is still in a characteristic. One has not really gotten to the point where one sets the distance relay simply based on the derived M, because one has to consider the classic approach in that sense. All right, that is the three questions, what, why, and how answered. Now we're going to go on with what we now have at this point. Remember this complex equation, and we're going to a little bit try and understand what are the factors or components to generate or come up with this complex equation, and how the distance protection fits into that. For that purpose, I'm using a simplified diagram here. You can see there's only the output part. It's symbolic now to explain what we are doing. It is not the exact representation of how distance relay will work, because we don't have the return part here. So it's just for explanation purposes. So the function is going to the distance relay will be set located here. It'll have a set reach, and it will then try and establish, is this a fault inside this set reach or outside? That is the requirements of how it will be doing what it has to be doing. That's its job, so to speak. It will be doing this by measuring obviously voltage and current. You can see voltage and current is measured, and then because it's numerical, we're talking about numerical relays now, it has a complex phasor, so it can take the equation you see on the complete side there, V, the measured voltage is equal, Kirchhoff again, I left times MZL. We have no fault resistance here, so we have a simplified, very simple equation at this side over here. For example, if the M over here is less than 1, it's internal here. For example, M round about 0.55 would be that red dot. And you can see the fault is exactly on the line impedance. Here, simple starting point. And clearly, we will trip for the internal fault because it's inside the set reach. If we now come to the problem that we know we will be facing, there is a fault resistance here. This fault resistance now creates some difficulty, because there will be a voltage drop on the fault resistance, not only due to the current coming from the left-hand side through the loop, but also for the current coming from the right-hand side through the loop. We have to look at the sum. I left plus I right will be flowing through the fault resistance. So if we extend our equation here, the equation, remember, it was I left times MZL. That was up to the fault location. We have to include in the voltage loop now the sum of the two currents, I left and I right, and that's a vector sum. You can see vector because there's a line underneath, times the fault resistance is real, no phasor, it's just a, but this sum of these two currents times the fault resistance create a voltage drop. And remember the measurement we used in the simple at the bottom was V divided by I left. The relay only has the I left current for the measurement, and if we divide this top equation by that, we will see here that the fault resistance is appearing as 1 plus I right over I left in the loop. So it is appearing over here. At this point, it's just shown as a real resistance, but you can see this is an assumption which will not always apply, because we have here a complex division, I right plus I left. This would only be true if the angle of I right and I left have the same angle, because then the ratio will be a real value. If the angles are different, you get a complex result, and that complex result would mean that this is going to be tilting up and down resistance measurement. Looking to that situation now, we take our diagram, we make it a little bit more colorful so we can see what's happening. And we take the fault away and we take our diagram and replace it with a load condition. So this is before the fault is happening. We're now going into a load condition and trying to see what is happening in this system if we have a load. It's a two-machine model. And if you have a load current, then it's interesting to get real power, because that's what the power system is there for. The load current should be in phase with the voltage. Right, there can be different scenarios. This is a very much simplified diagram, but for explanation, it is perfectly good enough. You can see the load current is shown here in the center, vertical, essentially in phase with the voltage. Okay, so not exactly in phase with the voltage. Why? Because the voltage has got different angles as you go through the system, because this load current will create a voltage drop across the series impedance. So from the complete left to the complete right, you have to take the total impedance Z sum over here. The Z sum is the sum of all the impedance you see here from left to right. And the voltage drop will essentially, because it's mainly a reactance, this Z is typically an X in a real system, very small R component is mainly an X. The voltage is going to be leading the current by 90 degrees, and that you can see that at the top here, that voltage at 90 degrees to the current is there. And that means from the left-hand side to the right-hand side, we have this angle difference. If the load increases, the angle will increase, and the load decreases, it goes down. That is this angle between the two sides referred to as a typical load angle. In a normal power system, we'll see with power swing in the following presentation, not today. In the other presentation, we'll talk about power swings. Obviously, in a stable system, this load angle will be less than 60 degrees. In the extreme situation, typically it'll be less than 40 degrees. And in Western European strongly meshed systems, you can probably get angles which are even much smaller than that, probably in the range of 20 degrees or less. So it is depending on your system. If you have got large distances between generation and load, you can have larger angles, but it's going to affect us. But if we come from this condition now, remember this angle difference here, and we now create a fault, but that's what typically will happen. You'll have load current, and then you'll get the fault condition. The fault condition now happening will create the current on left and right hand side to have an angle difference, because the current on the left side will come from the source on the left. Remember the voltage, the internal rotor EMF on the left hand side is the green voltage. We'll have a current, fault current about 90 degrees lagging that, which is the green current we see over here. And the same is happening on the other side, the right-hand side. That voltage on the right-hand side will have a fault current lagging it by about 88 or almost 90 degrees, depending on the power system. And that means the load angle is essentially defining also the angle between the fault currents from the left and right-hand side. That is what we'll often talk about, the load influence on the fault. It only comes via the fault resistance, because the influence of the remote fault current is only sensed in the fault resistor. The fault current on the left-hand side does not affect the loop as such. It only affects it on this section of the fault resistance here. And that we can see here in this equation. If we now divide the I right by I left, there's an angle difference between the two. And we'll see that on the next diagram. That division I right by I left will create a tilt up and down of the impedance. Complete other side, you can see it over there, tilting up and down of the impedance. If we are exporting load, as maybe from the left-hand side, it'll tilt down. If we were importing load, you would typically tilt up. And that you can see in this diagram is a problem. That's why we need to consider the load as such. All right, so we've gone through a few aspects explaining the distance protection localization, how it's going to measure, some of the problems it will be facing. We've used this definition of MZL to localize the fault in the loop equation. We've seen that the load current can affect the measurement via the fault resistance, and ultimately that is the explanation of distance protection. So if we come to this situation now to see how are we going to deal with this requirement, you can see I've rewritten the generalized loop equation at the top here. And you can see that we want to extract M to localize the fault, but there is a problem here. The fault current, which is flowing in the resistance, we don't know. The relay only has available the I loop A current. It does not know the current in the fault. So one needs to deal with this. So somehow this factor at the back here, I fault times RF, these are unknowns. They are inside the loop, but we don't know I fault. We don't obviously know R fault. And how would we deal with this? It is tilting up and down, as we saw. This We know the reason for that. That's because the two currents on the two sides are not in phase. Again, a different equation at the bottom here. BIA showing you the complex division multiplied by RF. That's the reason why it is tilting up and down. That gives us a delta and X, and that is not good because the delta and X will be our zone boundary and can give us selectivity problems. Remember, the zone 1 setting, for example, may not pick up on the external fault. So we need to consider that in our safety margin. So we now introduce for the first time the situation that you have to know which type of distance protection you're talking about. You can see the top in the heading, it says classic distance protection. The classic distance protection is going to take this loop equation here and make the assumption that this does not exist, okay? We can do this, say, all right, let's try and assume that it is not there initially. Then we can solve for M ignoring that, and then we have all the values, because the relay can measure all of this. The two currents flowing at the relay location, I loop A out, and the return current can measure, and the voltage can be measured. And then we know the ZL is a setting, so everything is known, we can calculate M. But the problem, the assumption would be that this M is on the line. But we know it's not because of the fault resistance. But the fault resistance, on the other hand, we know will just push the impedance into the first quadrant, as you can see there. So then you apply a setting, and we'll talk about that later on, a resistance reach setting to make allowance for that. So that is the ultimate result. So the classic distance protection will take this and make a resistance boundary setting. So the X boundary, we'll look at that later on, set for the reach. The R is set to consider the fault resistance. And we know there's some tilting up and down. We have to deal with that in another way, but the classic distance protection can deal with that. And there you can see for the classic distance, for that tilting up and down, you have the choice to set here the zone inclination angle, okay? And that you would typically use on a zone 1. And in the manual, there's some derivation where you can derive the setting for this angle depending on your load angle. Remember the load angle between the left and the right-hand side. Alternative to that, we have a distance protection with RMD. You can see the top in the heading. This is the reactance method distance protection. It starts with the same equation here, but it is not simply going to assume that this is not existent. It's going to use a mathematical method to compensate for this, to extract it, or so-called load compensation. And the technique, I don't want to go through it in too much detail. It is a complex mathematics. You take a I sub current, a substitution current, and the requirement for the substitution current is that it has the same angle as the fault current. Okay, so if you conjugate that current and you multiply this equation on both sides by that current, you can see it was done here. Makes the equation even a little bit longer. But you can do this, multiply the equation on both sides by the conjugated I sub, and then you take the imaginary component. And then the reason why you do all of this is because then this term over here will be equal to 0. Because the imaginary component of this term is 0, because if I sub and I fault have the same angle, then I fault times the conjugate of I sub will be a real, pure real, not have no imaginary part. So that will be 0. So that technique then, so if you then solve what is left over here, if this is 0, you can see there's no more I fault and R fault in there. We can solve this part of the equation like this and derive M independent of the resistance. This is the so-called reactance method distance protection. There's some difficulty in defining I sub, okay, but it's explained in other presentations in the manual. I just have one slide showing here. You have only one setting, because that's really at the end of the day the problem you have. What do I have to set in the relay? There's only one setting here. The setting applies for the ground loop. So in the ground loop, you have the choice whether you want to use the 0 sequence or the negative sequence current as the origin for the substitute current. The phase-to-phase fault will always be done with negative sequence. There's no setting required for that. And then you have compensation angles here. The compensation angles is a fairly complicated equation here. It's for non-homogeneous lines. Again, if you leave it on the default 0 degrees, then you assume a homogeneous system, which will be good enough or much better than doing nothing in 80% of the cases. But we have complicated situations. You can then set a compensation angle to even allow for non-homogeneous systems. All right. So which should you use? Now I've created some new difficulties for you, saying, okay, there are different RMD, classic distance protection. Which one should you select? You can see them here in the global library of Dixie 5. The classic you can use if you have a system with meshed, strongly meshed system like the Western European system over here. We've checked this with the utility over here, some historical data, and we compared. We did not really need an RMD. There was no need for load compensation. The faults were all measured very, very accurately with the classic. The RMD is strictly in countries or in areas where you have got long transmission lines, very large distances between your generation and your loads, geographically extensive distances and long transmission lines, and you get large load angles. That's where the RMD with the load compensation has got the big advantage, where one should use that. Generally speaking, I would say I would recommend to use RMD always. The classic only really where you say, okay, I have historic, I'm using an old application, I'm going forward to my new application, and I want to keep everything is the same as it always was. Then you say, okay, I use the classic, but it doesn't change anything that I had in CProtect 4 or even older relays. That would be the advantage. So we almost have everything defined. The X-reach, we spoke about directionality. The directionality is added as a separate measurement to the reach measurement. How is it defined? And here again, I've taken from the manual, the diagram. You can see that reach boundaries are defined fixed. You have basically the 30 degrees in the second quadrant there, and this minus 22 degrees in the fourth quadrant. For the forward reach, those are fixed directional boundaries. They are just defined like that. There is no setting for that. It's fixed. You don't have to modify that at any point. How is that determined and why do we need that? I think we have looked at this a few times. The directional requirement is obviously for the faults when they come very close to the relay location. Here shown the orange little circle there. The faults are very close to the relay. What will happen is the voltage will become very small, near zero. Ultimately, it could even be zero if the fault were a bolted fault right at the relay location. That means if the voltage were for that condition theoretically even zero, then you couldn't have no directionality, but it would simply be zero, and zero is zero, and you would not know if it was forward or reversed ultimately. But even for faults close to zero, the tolerances on the voltage would create difficulties, and one would have to worry about that a little bit, and that's why we have a direction measurement independent of the reach measurement. What alternatives do we have for direction measurement? Classically, I've just shown very simple examples here. In the middle, you can see the faulted voltage. Okay, as the fault moves closer to the relay, that VF will get smaller and smaller. And we want to replace it with a substitution, a polarizing quantity for direction measurement. The very widely used technique is the memory voltage. You can see here, you simply say, what was the voltage prior to the fault? I memorize that. And then when a fault happens, I use this memorized voltage for directionality. Because the directionality only needs to know angles, really. Is it in an angle range forward or an angle range reverse? So the magnitude doesn't matter. So the requirement then is obviously that the memory or the basically polarizing voltage has the same angle or a similar angle. We have large tolerances. You see, that's why you see the reach boundary going 30 degrees into the second quadrant and 22 degrees into the fourth quadrant. You have the directional boundaries are tolerant. They are not restrictive around the fault. To make allowance for any influences like this, it's not critical. So that is an important thing. An alternative to the memory is what is shown on the left there, the healthy phase. We did speak about that. Remember the Mohs circle, you had the choice, the memory voltage or healthy quadrature phase. The quadrature phase obviously does not apply to three-phase faults. Three-phase faults are a little bit difficult. But for all other asymmetrical faults, you will find a healthy phase, with either a phase 1 to ground fault, as we see here. The voltages L2 and 3 are healthy. They are not affected. And you can see the phase-to-phase voltage, 2, 3. If you rotate that by 90 degrees, you get that yellow phasor. And that yellow phasor can be used to replace, for example, the memory voltage. It's got the same angle as the memory voltage, can be used as a polarizing quantity. That's when we talk about direction measurement, you'll also sometimes hear other polarizing techniques. There are delta techniques and so on. There are a number of them. but one very common one is the symmetrical components. I've taken just a symbolic diagram over here. Phase A to ground here in symmetrical components, top positive, negative zero sequence system. And we would use maybe the negative or the zero sequence system, one of them, to do directional decision. And you can see here the fault location from where the relay is located over here. The fault is over here, a forward fault. And on these forward fault conditions, this I0 and V0 will give you a certain angle definition here. You can see which is clearly defined. And interestingly enough, it's independent of the fault resistance. This is a very, very dependable and very accurate direction measurement here, and it can be done in a very clear angle range. And the angle between these two is defined by the angle of the source impedance here. And exactly the same you could do in a negative sequence with a forward fault location. If a fault moves to the reverse, remember then this point will be behind the relay, and what will happen, this current will reverse here. The current will flip over to the other side, and you have a 180-degree switch between forward and reverse. Very, very dependable. The symmetrical components are a very, very useful tool to give you information about asymmetrical faults. All right. Ultimately, then, that technique, whichever one is used under, and you don't have any settings to worry about there, it is done automatically, will give you these two boundaries. So we'll have a reach setting. We'll see that later on. We'll have a resistance setting, which we'll talk about how to set the resistance reach. And then we have direction fixed by the direction measurement. And then all boundaries, all zone insides of the characteristic are defined. Good. That concludes our first session. And are there any questions at this point? And I hope there are a lot of questions.
Thanks, Gustav, for the interesting presentation about the distance protection, about the principles. Yes, we have some questions. Okay. There are some interesting questions here that are coming from the audience. First one, I think, is related with the basics. With the latest technology, can the fault location be declared according to kilometers, miles instead of zone? And the theory of the zone be quashed?
Yeah, this is an interesting question, but obviously the fault location is the fault locator to have an idea of where the fault is, to go and find it, is one aspect. That is a separate function in the relay. But I think what the question really is saying, can we simply say that the distance relay will pick up for the 100% fault and say it's inside or outside? And that is not essentially the way the distance protection works. Because at the end of the day, when we talk about protection, this is important. The protection makes a binary decision, trip or not to trip. Okay, and we need to define that. And the selectivity characteristic I showed early on with the zone 1, zone 2, you can see is that we need to classify an area, and the distance protection may say yes or no. Is it inside, trip, or is it outside, no trip? Was it inside, start the timer expires, trip or not? So simply making, I think what you are saying is simply simple situation that abstracting it. So you basically say, okay, I've just set the line data and the other things are automatically done. That one can think about, but it is not done at the moment because the user still wants to have some control over what the protection does. If you just simply set the line ZL and nothing, I say I apply distance protection and this is ZL, nothing else, then you have to trust that whoever the developer was makes the decision. Okay, the zone 1 will be 80%, the zone 2 will be 120%, and the time delay will be 300 milliseconds on. That is then fixed, but that would be too restrictive because there will be situation on a shorter line. We'll see that there are critical situations that the zone 2 must be bigger than 120%, and maybe the zone 1 must be smaller than 80%, and so on. So one cannot make a fixed decision like that. It's still, the user must still analyze the individual case and make a decision what his zone settings are.
Okay, thanks, Gustav. There is another here related also with the basics. What is the algorithm used for the distance calculation in transmission lines? Can we configure two same relays with different fault locator algorithms?
Again, this is interesting. When we talk about algorithm, obviously I showed the MO which would be one algorithm. We talked about the RMD, which would be another algorithm, and the classic. Those are three algorithms. You can apply these together, all right? Now the situation is, how can you combine them in one relay? Some applications say that they would want to use the MO for face-to-face faults and the quadrilateral or the classic or RMD for the face-to-ground faults. But that is not really a redundancy, because the one is for the one type of fault and the other one for the other type of fault. Mm-hmm. If you want the redundancy within one relay, then one can do this. The question is it really beneficial? But one can do it. You'd have to then make two characteristics, but the end of the day is on a transmission line, then you combine them as an OR logic. So for the over function, it is maybe you've got a bigger dependability. You have to then decide, is it dependability or security that you're interested in? But it is not typically done because there's an unnecessary complexity. Mm-hmm. You could do it if you wanted to.
That's important also to highlight that our protected device has three algorithms, basically. Yeah. The MO, the quadrilateral or the classical, and the RMD that you can choose.
You can choose, yeah.
Yeah, that's really interesting.
And you can combine them parallel,
yes. There is here related with this presentation that you have done, safety, security margin of distance zones, zone 1, zone 2, varies, have variation, depends on the load, max and min load, maximum and minimum load, or I'm grown, it's the B-base.
Yeah, this is a very good question. As we spoke about in the application area, we often assume that 80% for zone 1, 120% zone 2. But as I said, on a shorter line, you may want to vary this. If you get situation on very short lines, we may have to compensate here, make the zone 1 smaller. There are safety factor equation for that purpose that you can look at. One has to look at that in detail. When we do the example later on, I'll also show the zone symmetry requirement, and we can maybe look at that. But typically, the rule of thumb is normally used, and that applies 90% of the time, 99% of the time. But there are special cases we have to then compensate and use a bigger or smaller safety margin.
Okay. Here also we have another one related with the presentation that you have done. It's related with the frequency during a fault. Can the frequency of current and voltage be changed from 50 Hertz? Then the 5 milliseconds is not valid for 90 degrees, isn't it?
This is, we'll talk about this a little bit later on. Normally the frequency does not change during a fault, because in a normal power system, you have got a very large inertia, is the term you use. The inertia is given by large generations because it's a mechanical rotation. And during the fault duration of maybe the typical fault is only on for about 60 milliseconds or so if it's selectively cleared, and 60 milliseconds the frequency will not change. The frequency cannot jump. Its frequency is like a rotor angle cannot jump. The frequency cannot jump. Frequency can only start changing at a very slow rate. So that cannot happen. The problem there, or the difficulty is there, the non-conventional infeeds, the new renewables, the static infeeds from mainly from solar power, maybe. The wind farm, you have to depend on the wind generator a little bit, but it's an inverter fed, meaning it's a static infeed going through electronics. Inverter, there's no inertia in that. Inertia there is defined by the algorithm. So there one has to be careful. And in the presentation later on, we will look at that a little bit. There are special methods in the relay to compensate for the problem that can come from the static infeeds.
I'm going with the last one because now we are going to move to a break. There are a lot of questions here that we will try to answer in the other presentations. And if not, we will answer later on via email, okay? Mm-hmm. We should use distance as backup in case of losing connection between differential sites. That's something that
this is a classic modern application, especially you have the 7SL 87 or 86 relays. It's ideal for that purpose. We have got distance and differential in one device, and they supplement each other ideally because the differential being communication dependent, but very, very selective, can work ideally and very sensitively and selectively. But if the communication fails, you would want the distance as a backup. And the distance has other features. We'll see that in the presentation later on. For the transformer example, the remote backup functionality is to get the complete power system protection. So it's a perfect thing to do. If you have a differential protection and you have the means to put a distance as a backup, I would say, or main B, main 1, main A, main B, this differential distance, it's a perfect combination.
Yeah, it's also that I want to mention that the distance protection is a main protection, basically, for the line. That's really important. Then, unfortunately, we are out of the time for the first section. We will have a short break of 5 to 10 minutes for a coffee. Then we will start with the second part with the examples. Then see you in between 5 to 10 minutes. Okay.
Okay.
Thanks, Gustav.
See you then. Thank you, Jose.
Welcome back to our second part of today's webinars, distance protection examples. I'm sure that with these examples, many questions that you have will be answered. I saw in the chat that you have many questions, and now with these examples, Gustav for sure is going to answer your questions. And if not, then in the session of question and answers, we will answer. Okay, Gustav?
Thank you, Jose. I hope you had a break and are recovered. We now go into the next session, some examples. And again, I don't want to go just into Dixie screenshots. I will try to graphically show you how the distance protection copes with all sorts of requirements. If you're going to apply the distance protection, you can do this in all sorts of situations. Here we have, for example, one basic condition. Is your system grounded, isolated, or compensated? What does this mean? The grounded system means that the sources, okay, here we see on the left-hand side, is grounded. This grounding can be via an impedance of that nature, but it must be an effectively grounded system. The definition of effectively grounded will determine, basically during a ground fault, how much voltage rise you can have on the healthy phases. Other system treatments, start-point treatments, can be isolated, sometimes done in the lower medium voltage areas. Also, distance protection could be applied over there. Obviously, if you have a single-phase ground fault here, it is not a short circuit. It's treated as a ground fault, which must be detected with other techniques, not by the distance protection. Distance protection is only for short circuits, but the phase-to-phase and the other faults can be detected. And the final one you see is the compensated network, compensated, or sometimes called resonant grounded. And that would mean, like the Peterson coil you see over there, means that during a ground fault, you would ideally get only a very, very small fault in the current, fault current in the fault location, and the fault could even extinguish without the breakers opening. Ideally, that is a different treatment. Also, their distance protection can be applied. And there are, for this, as you see on the bottom left there, the selection is your distance protection in a grounded system or isolated or compensated. Effects in some parameters you have during ground faults. As I said, typically the isolated compensated, you will not trip during ground faults. You would basically only trip during cross-country faults. You've got two ground locations in that system, and you can have some phase preference. There are certain specific parameters for those in the distance protection there. But the more common, typical, is the one for grounded. You see at the top, distance protection for grounded systems. Your first selection, clearly you must decide which one to use over there. If you then, inside Dixie, and you then have your relay, and you take your product code or whichever means you have, and you create your new device inside Dixie, you will be faced with a template, and they are just highlighted this new feature here that you may not be aware of. You obviously have the standard templates which come with Dixie, but nowadays you can also create a user-defined template, which I would recommend if you apply a certain number of relays, that you then create a user template in which your pre-configurations are done, and you don't have to start from scratch every time you make a new relay. It would do that. The next aspect in the application of a distance protection is the CT and the VT connection. Within CProtect 5, you have got a number of possibilities to do this. Breaker and a half, you can have two CTs in the assignment and so on. I don't really want to go into all of those details. But roughly speaking, it is important for the distance protection to have the proper CT-VT settings and also to know what impact they can have on the distance protection mechanism operation. So here are some screenshots, very busy slide. Don't like those normally, but let's have a look. You see there on the left, there is the measurement point to the line, the two orange crosses there. So you have to obviously must assign a current and a voltage measuring point, at least one, to the line. Then you have on the other side, you can see the ratio settings for the CT and the VT. And this is interesting because then you come at the bottom left, you see the secondary, the reach setting of the distance relay. is in the edit mode secondary, the complete bottom left slide, you can see that. And this editing mode, you can change this in Dixie, but it shows you that you can have two different reach settings. So certain settings are affected whether they are primary or secondary. And you can see in the equations there, the conversion of a secondary to a primary or a primary to a secondary in this situation. So you have to know it is changed by the CT and the VT ratio. So be careful when you are applying settings to make sure that you have calculated a secondary value and setting it in the secondary mode. Or if you have a primary value, then change the setting mode to primary and apply it as a primary setting. You can set it in either. Dixie will automatically adjust it, but you must obviously set it in the correct manner, otherwise you could have an offset. Here in this example now, typical example condition, I'm just going to have a very, very broad example here. You see I have an overhead line. The overhead line has a certain length here, 15 kilometer in this situation. Then you'll see the typical parameters that you have for an overhead line, the positive sequence impedance and the zero sequence impedance given in R and X, and they are typically given in ohm per kilometer. And this is either measured, you can use a special Omicron, for example, equipment to measure the line impedance, or you would calculate it from some software. You could also do it by hand, old school, if you want, with equations, hyperbolic sine, cosine, very long equations you can calculate depending on the tower geometry and so on. The important thing is we see here that the line impedance is typically a parameter, fixed parameter per kilometer, so it's not varying. If we have a certain line construction, that is a constant parameter for the total line length. We'll see later on in the examples, this can change. If we have mixed feeders here, then this is not going to be constant over the entire line length. But here in this simple example, we still assume we have a homogeneous or line with one configuration from beginning to end with a certain impedance. These impedances we could then calculate a setting for zone 1. You see on the complete left, zone 1 reached 80%. We have that 20% safety margin. And then you can calculate that, the equation in the middle here. You can see the X would be 80% times the 15 kilometer times that 0.249 ohm per kilometer. That would then give you this end result here, a setting 2.988 ohm. But remember, these values were primary. Setting is in primary, so make sure that your setting mode is primary if you're going to set this value here. It is a primary impedance, or convert it to secondary if you wanted to. So that would give us our first boundary. So if we're going to do an application, that calculation gives us then our first boundary of the zone. We've just calculated the 20% safety margin for the zone 1. It's the X setting over here. Typically the easiest setting in distance relay to calculate. What about the resistance value here? That is unfortunately going to be not quite so simple. For the resistance setting, we have to know which type of fault we are looking at, and I'm taking the more complicated one, the phase to ground one. The phase-to-phase fault essentially is similar. You would calculate it here instead of with the phase-to-ground arc. With the phase-to-phase arc, you can see the length at the other side. They're 12 meters in this example for the phase-to-phase arc. And you would not have a tower footing resistance. The tower footing resistance you see here only applies to the phase-to-ground faults. So that's why doing in the example the phase-to-ground put it is the more complicated. For the arc, the same as for the phase-to-phase, you would calculate the arc voltage. For that purpose, we assume an arc length. The arc length we would derive from the tower geometry. You can see in this case we have a 5-meter insulator length that you can get there between the conductor and the tower, and that would typically be the path of the arc. But the arc it's a thermally very dynamic thing. I don't know if any of you have ever seen them live. I have seen it live in some simulation testing we once did. Or you can see videos of it here and there. These things are very dynamic. They are not just standing there. They are moving around, and it's thermal. Because it's a lot of magnetic and thermal activity in this arc, they tend to make a curved path. So we use here this 1.5 factor to make allowance for the fact that the arc is not going to go in a straight line through the 5 meters, but will go in a curved path. So we assume a 1.5 factor. The 2.5 kV or 2,500 volt per meter, that is the voltage of the arc. And this is interesting. You define an arc not like a normal Ohm's law, current voltage equals impedance, for example, that ratio. It is in the arc, you have a fixed voltage. If the current increases in the arc, you would typically find that the voltage would actually decrease. Remember, in the normal resistance, if you increase the current, the voltage will go up in a linear fashion. The ratio between current and voltage is linear in a normal resistance, not in an arc. An arc, the voltage is a value per meter. But it is ionized, basically gas and such, and the energy or the temperature of the gas goes up the more current you have. So actually the voltage per meter goes down if the energy or the temperature of the arc, so to speak, goes up. It's physics. We don't really need to go there. The 2.5 kV per meter is a very, very conservative estimate. We've seen simulations where you get smaller voltages, but typically not larger. So already that has got a big safety margin in it. We can say this is a very, very safe and commonly used. We've used this in our calculations for ever since I can remember in the distance protection. So with that, we can calculate the arc resistance. What we need, obviously, is the fault current. And this is not the fault current at the local relay. This is the fault current in the arc, essentially. But in terms of what the relay locally is measuring, we will see later on, we must be careful how we deal with the arc resistance in terms of local and remote in-feed. It is different to the tower footing resistance. Which brings us then to the tower footing resistance. This is something which is specific to the ground fault. Remember, on the face-to-face fault, the current is not going through ground. It's only going face-to-face. But on the face-to-ground fault, you will get the short-circuit current flowing through the tower footing resistance. At the top, we see here a symbolic line. And the line has the phase conductors, and it's got the ground conductor. You can see that on the roadside, obviously, the three phase conductors, and right at the top of the tower, the so-called screen wire or ground conductor. And the ground conductor will carry short circuit currents. So if you get the flash over here from the phase to the tower, some current will flow then obviously from the tower to the ground wire, but some current will flow down to the tower footing resistance. And the interesting thing is it will not only flow through that one tower, it will flow through the ground wire and then through the next tower and the next tower and the next tower. And so a number of towers will have current flowing through their tower footing resistances. So the effective tower footing resistance seen by the relay is not one, it's a number of tower footing resistances in parallel, but they don't all have the same magnitude of current. They've got different magnitudes. So the closest one, the biggest. And as you go further away from the fault location, the currents go down. This looks like a Gaussian distribution here of current. Difficult to calculate, and therefore you can take, normally we use a simple graphic representation for that. You can see here, this would be the ohm for one tower resistance. And this is something that is specified in the tower construction because it costs money. You have to ground the tower effectively. If you don't ground the tower effectively, then you need bigger spacings because if there are lightning strikes near the tower, you get the so-called potential rise near the lightning strike. And if the tower footing resistance are not fairly small, the rise will be very large, close to the lightning strike, and you'll get a backflash on the tower. And this is not good for power transmission. So it is a specification that you have a certain maximum magnitude of tower footing resistance. And you do this by burying electrodes in the ground or even putting copper mats under depending on the type of soil. It is part of tower construction. So we have a tower footing resistance, but that is not the value we need to use because it's all of them in parallel. And then it depends on how the ground wire is constructed. If you've got two ground wires, obviously more current this distribution here will be flatter, and you'll get a bigger parallel path influence and a smaller effective resistance. If you've got a single ground wire, this curve is a little bit steeper and the parallel resistance effect is not so big. But on the left-hand vertical scale, you can see we typically can use a value around about 2 ohms for a tower footing resistance would be applying to most cases a very satisfactory result can be used. The problem now is that for the fault, we have the two in series, the arc voltage and the tower footing resistance, and they are different. Remember, the tower footing resistance is a normal Ohm's law resistance, meaning the larger the current, the larger the voltage. It's acting like a real resistor, and the arc voltage is a fixed voltage. It looks like a resistor, but it is not affected by Ohm's law. So in this example, we make 3 kiloamps flow through the arc as measured by the relay. So we have a certain arc voltage, which we calculate at the top, and then the relay has got 3 kiloamps flowing there in this example, and then that means that voltage divided by the 3 kiloamps. This is what seen by the relay. Remember, we want to know the resistance as measured by the relay. So the relay would see this as a 6.28, 6.25 ohm in this example, with these values just substituted there. The tower footing, the arc resistance. We have to add the tower footing resistance to that. All right, and the tower footing resistance, effectively, we see at the bottom here, we read it off the curve, we use 2 ohms for this example, but the tower footing resistance will be affected by the remote in feed. So I just said in this example, 2 kiloamps, in the previous time we had 3 kiloamps here, but it's just an example, just to show you the influence. If we had 2 kiloamps, 2 kiloamps and 1 kiloamp left and right, then obviously you can see this 2 ohms is multiplied, becomes effectively 2.5 ohms as seen by our protection relay. If this was swapped around, that we were 1 kiloamps from the relay side and 2 kiloamps from the remote side, this ratio would be, other way around, would be 2, then we would be seeing 2 times that, we would be seeing 4 ohms. So you can see the weak in feed is more negatively affected by the tower footing resistance than the strong in feed. There's something we must remember. Sometimes we get sequential tripping, teleprotection arrangement, and so on. We must assume that you need a weak in feed logic also for that function. That sometimes the weak in feed side will have difficulty getting effective resistance coverage. That's one of the aspects why we have a weak in feed logic or weak in feed function in the teleprotection later on today. So to do the resistance setting now, we have to consider for the ground fault these 2 resistances in series here, and that gives us the total fault resistance. Remember, we have to calculate them carefully, the RTF, tower footing, with consideration of remote in feed. The R arc is not affected by the remote in feed, so we properly summate these 2 values, and then we need to see how is the relay going to measure them, because this is, remember, we have a outward and return path, and in the impedance path, the relay is only measuring the ZL. So, but this is, where is this fault resistance? Is it in the outward path or in the return path? And it is split into the 2. It is some of it. So from the relay measurement, it's split into 2. So we have to consider how is the relay going to measure that. And for that purpose, I just drew, so you can see the 3 phases here, and the return path now for the ground fault, the ZE is the return path. And we make a loop equation here quickly, just to show you this little bit of background. But before I do the loop equation here, I do a little trick here, and for the first time now we split the ZL into, as you see the equation at the top there, into RL plus JXL, and the ZE the same. We split it into its orthogonal real imaginary component. And then we define 2 ratios now, the so-called residual compensation factors, term sometimes used, or simply KR, KX, or in CPDEC 4, there were RERL, XEXL, but you can see the definition of those over there. Now, I didn't want to draw 5 equations on this slide here, so you can see I've rewritten this voltage loop equation here, including the KR, KX factors here. You can see if you look at this, just take the one example at the bottom for the resistance, for example, then obviously the resistance in that loop is going to be the voltage will equal to the RL times the outward current, which is going to be IC, but it's the C-phase current in this case. That's IC is the C-phase current. You can see that in the equation. So it's RL times IC, and then it is RL times IE, but no, it's not. It's IE times ZE, and you can see the minus sign Y and minus sign there because obviously you must remember that they're polarity. This is something you must be very careful of because this loop here is going in this clockwise direction and the IE is in opposite direction. So if we take the loop here and try and cross-trace with the finger quickly, go this way around. Whoops, difficult to do this like that. You can see the IE is pointing against the loop direction. That's why we need a minus sign there. That's for the IE is flowing, we consider all currents flowing into the line as being positive. So if you look at that, then what we really need to do here is IE times ZE, or basically IE times RE for when we look at the resistive component, and it must be negative because it's flowing in the opposite direction to the loop. Okay, but we don't do that. We simply say it is IE times KR. But if you look at KR at the top, you can see KR is RE. So if you say IE times KR is basically IE times RE over RL, and then outside the equation you have RL, you multiply RL inside, it cancels, and you can see it's IE times RE. So the loop equation is simplified by including these factors Kx, Kr, because those we can set. And if you look at this equation now here, you can see the relay can measure RL and XL and input it into the characteristic because it's the only unknowns. Everything else is measured or known as a setting. Kx, Kr are settings, IC, IE are measured, and VC are measured. So all the black values are measured, only the red is unknown, and we can solve that. If we solve this equation in numerical relay, we can determine the RL, XL, and for the location. And interesting enough, it's exactly the same RL, XL that you would have on the face-to-face fault. Remember the face-to-face fault, we just simply said that this is the impedance. So we make our setting based on this impedance, and we can ignore this impedance ZE down here because the influence of ZE is considered by these compensation factors. That is the reason why one does that. All right. If we now assume that there is now going to be a fault resistance added here, so now we have to make this loop equation that we just had in a nice simple manner over here, and we have to extend it with one further factor. And here I make a simplification just to the graph, and the simplification is the assumption you see there that IC equals minus IE. It's basically that the current flowing out here is the current equal to the current flowing back, and you see the sign minus because it's opposite direction. IC is out and IC comes down and flows opposite direction to IE. So IE equals minus IC. It's assuming that the remote side, the two loops are effectively left and right side are circulating the currents. There's no current flowing out and through the resistance and then onto the other side. We make that assumption. It is for explanation purposes, we can do that. Then we can realize that the relay measurement was obviously that voltage divided by basically the current effectively, and for that purpose we would then see that you would measure the resistance not directly, but the resistance divided by this factor 1 plus Kr. So this is important in the classic distance protection, is important in the classic distance protection. The fault resistance, this we see over here, is not measured directly. That sum of resistance is measured by the relay, but divided by the factor 1 plus Kr. It is effectively splitting this resistance, putting some of it into this return path and some of it into this path, and only what is in this path is what the relay would consider. So that would be what the relay measures. Okay. This is the setting we just looked at over here. I think now we are happy that we can set the boundary to make allowance for the resistance over here with that safety factor, but we have to obviously consider this factor in the measurement here. So we calculate the arc resistance, the tau fitting resistance in the graphics we showed early on. Then we summate them and we divide them by this 1 plus Kr, and that would be the setting we would require over here. So in this example, we had remember that was 6.25 ohms plus the 2.5 ohm, 8.75 ohms was the sum of these two. And then if we apply the setting, we put a 20% safety margin. You can see the orange equation on the right-hand side, 1.2 times the 8.75 ohms, but divided by 2. Okay, why? Because in this example, we would assume that the setting was, KRKX setting was basically 1. I'm just wondering if this is a face-to-face. No, it's a face-to-ground. Okay, so that would be the setting with the assumption here that the KRKX is equal to 2. Basically KR setting. Sorry, I got a bit distracted there. Okay, for the RMD, be careful now, that was the classic, and I must highlight this here. For the RMD calculates the reactance and will calculate the fault resistance in a different manner. Remember, the reactance method has the load compensation, and the load compensation technique is to compensate for the influence of the angle shift over here, and we'll calculate the reactance basically inside the ZL directly. So the location of the fault M independent of the resistance here. That is the initial step. That's the important step for the reactance method. But then, as we had the question earlier, to categorize this into a zone, because also for the RMD, we must set a resistance boundary. So we said, okay, for the RMD, we will calculate the RF separately as a separate calculation, and there it would calculate the RF directly, basically not split into ZL, ZE. So there you would not use this fact, it would not divide by KR. This is important. For RMD, typically the resistance, phase to ground resistance, is set sometimes twice as big as for the classic, because you don't have that division by KR. Okay, so here you can see the calculation of KR2. In the previous diagram, we divided by that setting KR2. Not so for the RMD. The RMD, you don't consider that. It's not included. All right, that is for the phase to ground. But what about the phase to phase? And here I make a very interesting diagram over here. And you must be very, very careful, okay? Because if you're going to draw fault resistance, you must decide, how, am I going to draw it like this? Here you can see the example for the phase to phase. And this is the common way of doing this in that technique. But remember, the phase to phase loop is going to, measure the impedance only in ZL. So this is split into two. That's why I actually prefer to draw the fault resistance like this. And you can see this RF, if you draw it like this, is effectively the phase to phase resistance divided by 2. Okay, but you go around the loop around here. Compared to orange, compared to that technique, it's a factor 2. And the relay would actually mirror this RF over here. So, but if you have defined your RF like this, then for the phase to phase, you have to divide this one by 2, because the relay will see effectively this RF, not that one. And it's important because on the 3-phase fault, you cannot really use this orange designation. You'd have to basically draw 3 resistances here, like a delta connection of the fault resistance. It's not that practical. You could do it for a pure 3-phase fault, but what if you had a 3-phase to ground fault? It would be not possible. 3-phase to ground fault, you'd have to have a ground connection here. So for the 3-phase fault, we assume this definition, and for the phase to phase this way, and then they are comparable. So if you have a 3-phase fault, the fault resistance definition is exactly the same as for the 2-phase, but it's this black one, not this orange one. That is what's measured. So if you see a diagram like this, then you'd actually be measuring only half that, and your setting would be half this orange one, or effectively this is the setting you would require for phase to phase. Okay, so we have now defined the reach settings for the resistance. We defined the X setting for the zone 1 in this example. We still have some issues with the direction boundaries. We saw that earlier, the direction is fixed. You don't set any direction boundaries, but we have got this angle here. This angle still needs to be set. How do we determine this angle setting over here? It's a so-called characteristic angle. And if you look here, just to summarize again, the direction from the relay manual, this was 30 degrees in the second quadrant to minus 22 degrees in the fourth quadrant. So those are given, but we are still left with this angle over here. And this angle over here, you can see, is typically set the same as this angle here. Now, what are these angles? This angle is blue angle here at the top is the line angle. It's based on the X to R of the line. So you can see here the ZL will have a certain resistance R and will have a certain X. And with the arctan of the X over R, you can calculate this angle over here, the line angle. In this case, 86.7 degrees. And typically, we would set this angle identical. Here you can see it's set differently. It's set 85 degrees. But normally, in the classic distance, they would set these ones the same. Okay. Why do we set them the same? But if we set them the same, that would mean that these two lines are parallel. Okay, the blue and orange line here. And then that means the R setting you have applied at the bottom here would apply at all locations on the line. Because if these two lines are parallel, I mean they have the same angle here, then this R set is the same over the entire line length. And that is what we really want. We want to have resistance coverage for all locations inside the zone, and that you achieve by setting those angles the same. There are some conditions. They say, why don't we just take this away and make it automatically the same as that? There are some applications on cables where you get very small line angles. There you might go back to the old 90-degree setting over here. And I say, you cannot apply this normal law to everything. There are always exceptions. And some on cables, you might have a 40-degree angle here for the line, which would be really steep out here. Then you set the resistance boundary to 90 degrees. That would be, but that's not the normal application, it's the unusual application. All right, and just as we are finished and think we have everything easily sorted away, we come to the symmetry requirement. The symmetry requirement is based on what we see here, the R and the X setting, but we have now calculated based on the fault resistance and the reach, the line length. We've got these two settings, X and R, but the ratio you can see here, given as the R to X ratio, that's a critical one. If that becomes a big ratio, we get into difficulties. So what do we see in this diagram over here? In this diagram, we see a normal graph, and we have applied a zone boundary, the red one for zone 1 here at 80%. You see the ZL on the remote side, the black line is the line impedance. And if we make the first circle you see right at the end of ZL there, that would be the measuring tolerance. You can see the measuring tolerance for this graph is 10%. Typically, the measuring tolerances are less than that, so the circle is a bit smaller, but maybe if we include all safety margins, we include basically in the 10%, we say that all influences are in there for this graphic example. Now you can see the fault moves. This black here is a remote busbar fault. And remember, the zone 1 may never pick up on the external faults. That's our definition from this morning. Zone 1 must never trip on the external fault, and the external fault is a fault on the remote busbar. So we now include resistance in the fault on the remote busbar, then it will move away from where the ZL is on the left there along this line. The fault is always on the remote busbar, so it's always on this point here. And everything is measured perfectly, but we have a tolerance. And you see, as the impedance is getting bigger and bigger, the circle is getting bigger and bigger because the tolerance is a percentage of the impedance. And you can see the impedance here is about double what the impedance was at the beginning. That's why the circle here is now double the magnitude it was at the beginning and can infringe. So if you have a zone 1 setting that comes to the dotted line here, you can see here that measuring tolerance could make you think the impedance is inside zone 1 and you get a non-selective trip. That's why we have to worry about symmetry. We cannot just set the R setting to a huge value, because at some point it's going to create problems. At the bottom, you can see the 1, 2, 3. That's just not just the numbering 1, 2, 3. It is the value of the ratio here. So the first one, there's 1. The ratio is 1. X and R are the same. That's why the ratio is 1. You get that red characteristic. And the dotted characteristic is somewhere between 2 and 3. You can see somewhere between 2 and 3, we start getting an infringement over here. It's extreme. Remember, the 10% is just don't take this as a black and white rule. This is just a graph explaining with a graphic 10% value as an explanation. In the manual, you will find a table like this over here, and you can see here some R to X ratio recommendations. It's the recommendation, not a rule. And you can see here, 100 kilometer line, we get this 1 to 2. Remember, the 2 was the ratio R to X in the previous diagram. And you can see on shorter lines, cables, we go up to 5. 5 for classic would be the range. Remember, the phase to ground setting on the RMD is bigger, so there you can almost double the requirement here. For the phase to ground on the RMD, you can use it. These values in the table are about double what you have there. That's just a note to remember. But this table was done still for classic distance protection. For the RMD, you can double the ratio effectively. And just to have a graph here, you can see here now, if we assume 2 is our maximum value here, and you can see this drawn here in red, that would be the boundary 2 over there. And we can see we basically, assuming the 10% tolerance, we would not have a problem with 2. If that is an issue, again, remember that load compensation we set to zone 1, you can tilt the zone 1 characteristic down as well. But normally that's not done for this purpose, that's done for the load encroachment. All right. That is interesting for normal application, but I said there are obviously special conditions, and we want to look a little bit at some special conditions. And one special condition is the mixed feeder. And the mixed feeders are different reasons for mixed feeders. We have been getting more and more of them these days as people go underground near rural areas and so on. But whatever the reason is, the distance protection must cope with that. Okay, you can see here, obviously, this is an interesting case, line differential and distance protection. The line differential is not really affected by the mixed feeder because it just needs to know charging current over the total system. It's fairly immune to it. But the distance protection, the zone boundaries can be influenced. Because you can see now the zone 1 at the bottom will have some cable and some overhead line in it. They have different angles. And as we saw, the angle settings and so on can be important for the distance protection. how do we deal with that? Because we don't have one line angle setting here, or we don't have one KR setting. The cable and the overhead line have got different KR and KX values. So we have to deal with that somehow. And the way you deal with that is you set the value at the zone boundary. And this is a technique. I've shown it here graphically. You can also do it with equations. And there's an application note that this presentation is also then based on, that you can find if you are interested to read up on that, more details how to do that. The principle is that you would define the zone 1 boundary, and you define this as a certain physical point, in other words, kilometer. You can see here it's at the bottom at around about 100, and I didn't write it in here, probably 105 or 6 kilometers, somewhere there is the zone 1 boundary. For this, you would calculate based on the X setting. The way we always did it, 80% of the total X. So you take all the X of cable 1, overhead line, cable 2, a certain X, then you set your zone 1 to 80% of that, and that would give you then a physical location here based on the X. That is your physical zone 1 boundary. Then at that boundary, you would then look what is the effective value of the R0 and X0 and the R1, X1, etc. at that location, because with those you would calculate then the KX, KR. And I think we have here an example. Why is that important? Because if you have a classic relay down here, you can see in the calculation of the reach, the X reach, which is the critical one, you have got the factors KR, KX. They will affect the way the reach you have to the fault. And in the RMD, it's even more critical maybe, because the K0, okay, the K0 is essentially a complex KR, KX. It's really the same. Affects it. The line angle affects it, but also the line angle is not constant. And even if you are applying compensation factors here, they will also be affected by the location of the line. So there are even more factors which need to be calculated zone specifically on the RMD. And there's an example now for the KR. I think I did here. That's right. The KR for the zone 1. Remember the zone 1 boundary here was at the 86.21 kilometer, but this is on the overhead line, okay? So you can see you have 20 kilometers at the beginning, complete left there of cable, and then you've got 86.21 kilometer of overhead line, so a total distance would be 106.2 kilometers here. That's the point you see over here from the beginning. So 20 kilometers cable, and then 86 kilometer line. That is the physical zone 1 boundary. And at that boundary, you would then take the R0 and the R1 at that physical location and calculate your KR for zone 1. That would be the zone 1 KR is calculated at the zone boundary. At the zone boundary, you need the accuracy. If the fault is closer, deeper inside zone 1, if you have got a deviation, it doesn't matter. The fault will be clearly inside zone 1. If the fault is outside zone 1, if it's very close here, you need to be very accurate. But as you get further away, you can allow bigger tolerances. You only have to be perfect at the boundary. That's why we calculate the setting at the boundary. And that was done over here for the zone 1. And you get these two values here. They are the equations, how to calculate the values. You don't have to read it off graphically. You can calculate with the equation. And you would use these in the equation at the bottom to calculate it. That would be the boundary. So this would be the KR setting applicable to the zone 1 boundary. And that you would then set in a classic distance relay. You would go here and say, I want the zone specific setting in my zone 1. This is a zone 1 setting. You say, yes, here I want zone specific. Then you go to KR and KX setting specifically for that zone. And you would do the same for a zone 2 and whatever other zones you have. If you are using an RMD, remember in the RMD, it was not only the KR, KX that are affected by that point, but it was also the line angle is affected by that, and the characteristic angle here, and also the compensation factors are affected by that. And for that purpose, you set the RMD to advanced. And if you have advanced here, you can set zone specifically all these parameters there. That would be applicable for mixed feeders, for example. All right, that was basically as far as much I want to say about the mixed feed application and the special consideration of the KR and so on settings in that environment. This is now going on to another special case that we had in one of the questions about the frequency. Is there frequency stability then maybe, and I spoke about the inverter in feeds and so on, and how we cope with that and deal with that. And let's have a look quickly at the difference here between a conventional on the left and a renewable in feed, and how the protection can deal with that. If we look at this, the conventional in feed on the left-hand side is large turbo generators, typically mechanical rotating objects that have a lot of inertia. That means inertia means you cannot accelerate it very quickly or slowly. It's like a train. You can imagine it's like if you take a bicycle, you can hit the brakes, you can stop in maybe a few meters if you're not going too quickly. But if you have a train cannot, or a big tanker cannot stop immediately. It needs a long time. This is what this is. You cannot immediately stop or make the rotational speed of the generator change. The inertia is there. Not so over here. If we have a static coupled thing, you can see it here, a little bit the diode symbol here, the inverter fed situation, it is static. Also from the name, you can see here it's not static, it is moving. It's a rotational, it's a mechanical in feed, moving in feed, as compared to a static in feed. Static in feed is a solid state electronic in feed as such, thyristors or whatever these modern coupling techniques are. Solar, the wind farms, to a degree, maybe one has to be careful. There are different types of wind generators, but I don't want to get into that now. If we look at our two machine model that we used this morning a few times, now we assume that on the left-hand side, we have this mechanical classic in feed with inertia. And then you can say that what do we know? That the voltage is stable. So if there's a fault now going to happen in the line here, the source on the left, the classic in feed, the rotor angle, the blue voltage is not going to jump. We saw that earlier. The motor is going to keep turning at the same speed as before. The frequency is not going to change. The angle is not going to jump. Nothing's going to happen. It is a strong in feed. There will be significant short circuit current in feed. The short circuit current is defined, and we would have clear also sequence components and so on. It's a very, very clear and well understood environment. On the inverter in feed side, it is more difficult, because the inverter needs some algorithm, some software to tell it what to do when the fault happens, but the voltage is going to disappear. There were some cases where you then simply shut down the inverter, said, we don't know what's happening, shut it down. It was a very common technique used in the early days of renewable in feeds to say if the voltage goes away on the network side, the inverter in feed is shut down to wait for the voltage to come back and then reconnect to that. Nowadays, you have certain fault ride-through algorithms which define how the inverter in feed does what it does during a fault condition. And there, one has to be careful what it's going to do. Why can it be a problem for the protection? We'll have a look at that over here. Okay, clearly on the classic side, it's no problem. The voltage angle is stable. We have defined negative sequence. Remember the sequence components for direction decision and so on. Also for the RMD to determine the load compensation and so on. We need to have a clear definition of that. We have a strong in feed typically. We have stable short circuit currents. The frequency does not change. That means the memory direction criteria is clear. The negative sequence criteria are clear. And we have a stable fault condition. What happens on the static side? It's obviously going to be different. Okay. The voltage angle is not stable. You could, in theory, here jump this voltage angle from one inside a cycle effectively. It doesn't need a cycle. It can jump instantaneously, almost the voltage angle, not quite, but almost. You can define a negative sequence during the fault condition. You need to define what to do. There are certain fault ride-through techniques which define how the negative sequence should look during a fault. So you try and synthesize on this side what a classic in feed would do. That's what one is trying to do now. Weak in feed, you don't have really a short circuit. Strong short circuit in feed, it's only really doing active power. There's not really reactive power. Again, fault ride-through might define what your power factor or your angle is that you're going to feed during a fault and so on. The frequency may change. Obviously, there's no frequency stability, but there's no inertia in that system. So memory direction, not always okay. Negative sequence, not clear what's going to happen because it depends on how the fault ride-through is defined. The fault detection, difficult because it's a weak in-feed condition. The criteria change during the fault. This is really not good. It's changing during the fault. So you can see the renewables can create a lot of difficulty for distance protection in theory. So how does one deal with that? We have a solution in CPROTECT 5, and the CPROTECT 5 is our the solution for all critical situations. We go to a certain so-called multi-criteria technique. Before I get to that, let's just look at the classic way of doing things. The classic way of doing things was basically with a selection tree. We have got a number of criteria. You can imagine each of these color blocks is different criteria. Maybe the one is a angle criteria, the one might be negative sequence criteria, the one might be a voltage criteria, and so on, impedance criteria, a lot of criteria, delta criteria, and so on. They're all here. But the interesting thing is here, you come to the selection logic, you look at the first criteria and say, is there the phase current bigger than the ground current, or is ground current large enough? Then you say ground fault or not ground fault, and then you go to other criteria and you end up with a decision down here. The point is you could miss, maybe that light blue criteria might be a very strong, dependable criteria, but you never even reach it because you decided early on that you're going to go down this branch. You never get the information from that light blue criteria. It's a branch or a decision tree that you make. Classic way of doing this in a classic Boolean type logic environment. You may know these logic diagrams from old software that written like that is technique. What we do now is we apply a multi-criteria technique, which in essence you see on the left-hand side could have the same criteria as the old technique, but they are not in a tree now. They are just evaluated and they give the result with a certain weighting factor into the end result like that. So criteria will never be excluded. Okay, initially all criteria will be able to give their result to the selection logic. So nothing is excluded by the selection path. You give this uncertainty, you give a weighting, something that's called uncertainty here, but I would call it a weighting factor. Say I'm a clear yes, or I'm not sure, somewhere between 0 and 1. You say 0, I have no information. 0.5, say I'm pretty sure. 0.9, I'm very sure that I can tell you what is happening. That's just a weighting factor. It also gives a correct result if situations are difficult. We see some examples in the very extreme conditions. This extracting and evaluating everything in parallel can extract information out of extremely difficult conditions and give you a result which with a plain eye you would not even have been able to see. And important here, it is also suitable for inverter in feeds if we know the control strategy to a certain extent, and that we do know. Because the fault ride-through techniques are now defined, and we can deal with those inverter in feeds. It's already implemented, tested, and it's running in the distance protection with the RMD technique is using this for a long time now. From the beginning of the RMD, essentially, it's been using this. It's not new in that sense. So how does it work? You can see all the criteria run in parallel. You can see each criteria here is running to, and then you have a certain weighting here, and then over here you get the 8 loops you can have. Sorry, the 7 loops, the 3-phase to ground loops, the 3-phase to phase loops, and the 3-phase loop. The 3-phase loop, interesting enough, is a separate loop nowadays. In the past, we'd only had 3-phase to ground loops and 3-phase to phase loops. Now we have got those 6, 3-phase to ground, 3-phase to phase, and the 7th loop, the 3-phase loop. The 3-phase loop is treated as an independent detection. In this example, you see the 10 possible types of fault you can get. Okay, so there are those 7 loops, but the fault combination, you can see the 2-phase can be combined with ground or without ground. The 3-phase we don't consider with or without ground, but the 3-phase to phase loops can be with or without ground. So that takes a 7 and makes 10 out of them because we have 3 additional fault types: 3-phase to ground, 2-phase to ground, or 2-phase without ground. It's a clear definition there. In this example, you can see here, for example, would be all the criteria or all the loops get some weighting, but it's clearly in this example, complete left-hand side, the L1 to ground has got the highest, by far the biggest magnitude, and the selection would clearly say, yes, it is an L1 to ground fault, because all the others see a little bit. Remember, an L2 to ground would also see some ground criteria. See, it's a ground fault, so it could be L2 to ground, but that's the only thing it has is some ground current. nothing else. The voltage and so on would not confirm that, so the L1 would be selected. But we'll see that maybe more effectively in a graphic form just now. Here's one criteria, a voltage magnitude criteria as an example, and you can see, obviously, if the voltage magnitude here is not decaying, remember this would be rated voltage 1, and the voltage during the fault only drops a little bit, then you would say, okay, I could be a fault, but very small uncertainty, only a very small quality, 0.1 or less. If, however, the voltage drops down to a very small value, all the way down to 25% in this example, from full voltage 1 down to 25% voltage, for example, then it is a strong criteria, and it'll give you a quality almost of 1. To say this phase must be faulted. This is clear. If this is the A phase voltage, then the A phase must be faulted. Otherwise, the voltage on the A phase would not drop to 25%. The voltage criteria is strong. And this would happen during a weak in feed. Remember, if you have a weak in feed, then you have a severe voltage drop. Okay, if you have a strong in feed, and it's a little bit remote fault and so on, you could have a smaller voltage drop. So you can see this is an interesting technique over here. Look at the current, it's going to be the opposite. In the current, you can see if the current is a small value close, smaller than rated voltage, 1 would be nominal voltage, then the current is a weak criteria, gives you only 10% quality. But if the current is like here, bigger than 4 times rated current, it's a strong criteria. So this would be the strong in feed. Remember the voltage was the opposite. So the criteria complement each other. If the one criteria is good for one network condition, the other criteria might be poor, then it'll be the other way around in a different network condition. So that, and you can see this here, clear fault condition due to the current, strong quality, a weak fault condition. You can see here, the current only goes up, stays at, it was a really small current, but the fact that it went up a little bit, if you did a delta in here, obviously you would see that increase, the delta here would, the delta criteria on the current here would be quite strong, because you get a significant increase of the current. So remember, there are also delta criteria, which I did not explicitly show here, but they also work in parallel, making up the 11 or 12 criteria we have. And here's an example. This is an L1 to ground fault. I think clearly to be seen, you can see the L1 voltage disappears here, and you get current only in L1, and you can see the criteria here, L1 to ground goes up to almost 100%. Clearly in all the other criteria are somewhere down. The loop selection just selects L1 to ground. It was easy as such, okay, to detect that. Other conditions are more difficult. I don't want to go to too many examples now. The same also applies in the area of direction determination, because remember, the direction determination can be affected. For example, the frequency stability was one issue. The angle, the jump of an angle could be a problem for direction criteria. So on the direction, we also do a multi-criteria technique. And you can see there some examples. Self-polarization, it's a self, like the, remember, self-polarized Mohs circle as an example. The memory polarization to offset the Mohs circle we had. The cross-polarization as an alternative to the memory voltage. And there are other techniques here, delta techniques. Remember, we saw the negative sequence or the zero sequence voltages for direction decision. And basically, all of those are working in parallel in the same way. And you summate them, and you then would use, based on the weighting factor, you see for each loop, you get a decision, okay, it's clearly forward, reverse, unknown, not sure. So it will be a forward decision here, because that technique works in parallel with all the others. All right, that was the special cases for the distance protection. Are there any questions in that environment?
Yes, Gustav, we have some questions from the audience here. I select some from the beginning also, because we're related with this chapter. Then, for example, how C-Protect 5 relays takes the fault inception angle into consideration, especially in the fault location.
All right. In terms of the fault inception angle is not considered by the distance protection, because it is not something you can control, and it has not got a meaningful impact. It will affect maybe the DC offset level of the current, but the filters will take care of that. The fault location would also try to avoid the influence of the fault inception angle by trying to get a jump free, try to move the measuring window in which it's going to make its measurement close to the reset where you are out of the transients. The fault inception angle only affects the transients during the first period, and the filtering will take care of that, as we saw early on.
Here we have another one from AC. Here the question is related with the parallel line compensation. Here I also read another question that traditionally we use the parallel line compensation for 2 lines, but now in modern lines we have up to 4 lines in one tower.
Yeah.
Then what?
This is obviously not really compensatable in such a sense. We only make allowance for a double circuit line effectively, where you can take for the zero sequence influence of the parallel line, you can compensate by measuring the ground current of the parallel line. If you got multiple parallel lines, then it is not really going to be possible to do this in an acceptable complexity. I think you could, if you wanted to, you could summate the zero sequence current of all the parallel lines and try and come up with a coupling factor, but the weighting is going to be different. You would have to require about, I wouldn't imagine it, but if you had 3 parallel lines, you'd need about a matrix of settings. You'd have to obviously multiply the number of compensation parameter settings by 6. The complexity is not given. What you do in that environment, you have to obviously compromise the reach setting. You have to then, with network modeling, understand what is the maximum influence of the parallel line and reduce your zone 1 setting to avoid overreach and make sure that your zone 2 is overreaching. You would have obviously there a smaller than 80% setting. That's what I was saying earlier. Certain applications require specific settings, and for parallel lines, you would have to reduce your zone 1 setting if it's on 1 circuit. Obviously, this is and the other problem is typically if you have got 4 parallel lines, they will not be parallel for the total line length. The more common thing is that as lines cross, you'll have a section of the line where you have got parallel feeds and you don't even have access to the measurement of that current. So this multiple circuit lines you have to consider in simulation studies and make your zone settings accordingly. It's not done inside the relay.
Okay. Here there are 2 questions related with renewables. One question is related with the solar farms, how these inverters sources affect the distance protection. And there is another one related with which method would you recommend for wind farms where the system is highly capacitive?
Right. We have to consider different questions in this environment. Obviously, what we were looking at now was the influence on the in-feed condition. There are other things that happen in the presence of wind farms. You can have, depending on offshore, we have situations with offshore wind farms with a lot of cables in the network. Is the one aspect. You get a larger charging current that you may have to consider. And if you at the same time your grounding is no longer effectively grounded, you have to make some special techniques. What we have done there that one has to look at very carefully is there's an application note for that to stabilize the direction measurement, because that capacitive current can affect the direction measurement. But this is very specific for extensive offshore wind farms. We've got a lot of cables. The cables have got a lot of capacitance. And the capacitive current was of a similar or larger magnitude than the fault current. We have resistive grounding. But I think that's the one aspect that you have to, on a classic sense, have to worry about. The other aspect is obviously the inverter in feeds. As I said, you must define a fault right through, and that depends. Most inverter in feeds are decoupled from where the distance relay is. But if the utility has a microgrid management, and they have to obviously, if a certain microgrid has got a lot of static in feeds, then you may have to consider to define a fault right through. They have to define what will these inverter in feeds during a fault, and that is programmed into them, the fault right through. What negative sequence in feed do they give under asymmetrical fault conditions and so on, and what do they do under 3-phase faults? They change to a reactive in feed to basically not just to substitute the voltage, which you would normally do, but to have a certain defined angle in feed. This is part of the renewable strategy that you have to worry about.
Okay, we have a lot of questions. I'm glad that we have a lot of questions here in the chat. But now, as we are running out of the time, we will have a short break of 5 to 10 minutes. Then we will start with the third part that is related with the special applications. Now we go with the break for 5 to 10 minutes and see you later.
See you later.
Welcome back to our third and last part of our webinar today. C-Protect Distance Protection Special Applications. And don't forget to put your questions in the chat or in the questions and answer box, and we will answer at the end of the presentation or via the chat or via email. Gustav?
Thank you, Jose. Right, we've almost made it. Then it's lunch for most of us, but one more session we have got to go. But I think it's a very interesting session for some new things that I think maybe some of you have not seen before. And there you can see a power transformer, not normally what we will be protecting with a distance protection, but I will show you here that we have got a special function, impedance protection for that purpose, and also show you the reason and the advantage of that compared to a distance protection in this environment. And for that purpose, I've used a example, and this example will follow basically, the step-by-step engineering, which is standard with C-Protect 5, and you can get, by combining different functions, a very effective and efficient solution optimized. So you don't have to really make compromises as one used to do in the past. You can really choose the best function for each purpose as you need it. An example I'm going to use to show this is what you see here, a typical medium voltage transformer. This example, 20 MVA, and you'll find that typically, especially what we see in the bottom here, the renewable generations, often these transformers are reaching their limits, and nowadays often in this environment where it used to be 20 MVAs, one goes up to 40 MVA to make allowance for not the consumption down here, but the generation in some sense, which creates new difficulties in applying protection. But let's go for it step by step and not get ahead of myself, as I sometimes do. We are applying here a relay, all right? I'm calling it a relay because it's not only a distance protection, and this relay is applied here on the LV side of the transformer. This is very commonly done in some utilities, and I'll show the advantage and the reason for this and the really strength of having this application. This relay has got two primary functions. One is to do protection in the direction towards the medium voltage system, but also to give some backup protection for this transformer for certain in-feed conditions, especially from these renewables down here. And we'll look at this here. We'll apply zone 1 into this area and a zone 2, again, two zones. But these two zones have got a different requirement as they would have had what we spoke about this morning, the zone 1-2 selectivity on a normal application. This is a different application of the distance protection. The zone 1 you see here is backing up the busbar protection, because here on the medium voltage you typically won't have a busbar protection, but you want to obviously have fault clearance of the busbar protection as fast as possible, and we'll do that with a reverse interlocking scheme down here. And the zone 2 is doing backup protection for these feeders, and that is an extremely important function, which we'll see just now again. It is not just backup, it is backup, very important. Then we have the zone 3 backup for the transformer. Maybe you have 20 MVA. Could be sometimes people would put in a dedicated transformer differential there. Some people would not. It's on the boundary. Depending on some, it's a transformer size decision. Doesn't really matter. But anyway, you can have this protection also doing backup for the transformer. And this backup is in two zones, 3 and 4. One is an underreaching into the transformer, and the zone 4 even reaches up here for certain conditions through the transformer. And we'll see there is special requirements here. Normal distance protection might not be ideal for that transformer backup. But before we get there, let's go step by step. The zone 1, a busbar protection as such, done with reverse interlocking, that you can coordinate with the feeders. So the reverse interlocking principle will get pickup signals from all the feeders here, which would block here, and this zone 1 must be coordinated with these down here, that it does not reach into an area where it will not get blocked, then it would be not selective. So the purpose would be that it would see the busbar fault, surely. It will also see some other faults in the feeders, but if it sees a feeder fault, it will get a blocking signal from the feeder protection. So the feeder protection must be more sensitive than the zone 1 over here. That is the requirement for the reverse interlocking. The zone 2 over here is doing a backup protection for these feeders. And as I said, this is a very important, maybe the most important functionality of this protection here, is because these MV bays will have a single trip coil, a single protection, and basically no backup. There's not a main 2 on a medium voltage feeder. It's only a main 1. So if there's a failure of this protection, or if there's a failure of the breaker, the trip coil, or something on the feeder over here, there must be a backup. Somebody must do that. And this is a task of this transformer in feed. This transformer in feed is the, one would call that a remote backup for this feeder, but it's not the same relay. It is kind of a little bit remote from where that feeder's backup functionality. And that is a difficult task, as we'll see later on over here, because it needs to get a very sensitive setting in the distance protection. Then we're going to have here this transformer protection, as I said, an underreaching zone 3 into the transformer as a backup transformer protection, and a zone 4. The difficulty here is, especially if you look at the zone 4 protection, the fault on the other winding here will be decoupled. The transformer will remove, for example, the zero sequence, and you would not get any zero sequence from the top system coupled into the bottom. So if there's a ground fault here, there will be no zero sequence voltage or current on the LV side, which can be difficult. Remember, we're expecting sequence components in a normal protection as such. The zone coordination is then the next step we will look at. Okay, so we've clearly identified what we are doing here. This relay is applied here on the LV side of the breaker, and it's really got a multiple tasks to do. And how are we going to implement all those tasks here and get the job done? Starting off with the zone 1. The zone 1, as we said, must be sensitive, but it may not overreach what the feeder protections are seeing. So we must check the feeder protection. And here you would have an overcurrent setting. And we remember this morning we had the circle characteristic. And the circle characteristic was defined by a voltage and a current. And effectively, we can draw this overcurrent protection here as a circle characteristic, where the radius of the circle is defined by the overcurrent setting of this relay. And we can coordinate our zone 1, that the zone 1 does not overreach that. And that way we are sure that the zone 1 will not pick up for a fault that the feeder protection cannot see. It's a very, very high security in this for our bus bar protection. What we want, but we don't want accidental bus clearance for a feeder fault, and that we get done in this job. So it is really fairly, and we don't need a really big zone 1 setting, but the zone 1 setting must only cover the bus bar fault. The biggest difficulty for the zone 1 is to get sufficient resistive reach for a resistance fault on the bus bar. All right, the difficult one is the zone 2. The zone 2 must see a remote fault on the feeder. If this feeder protection fails, maybe there's a breaker failure, maybe the relay has failed, there's power supply failure in the feeder relay, then we need to have a trip by the backup, which is the transformer in feed. Otherwise, nobody feels responsible for it. Who's going to clear this fault if the feeder protection has failed? We have to rely on the backup protection. All right, and that is difficult because we have a coordination of load and fault in feeds. You can see here at the bottom, the feeder might have a 300 amp load current, and the according setting may be set to 400 amps to coordinate with the load, tripping at 400 amps down there, and the fault, the load current on the transformer, all the feeders in parallel. If you have a 40 MVA, I can now see I've gone up to 40 MVA with the transformer. That's typically what's happening. You get 1,000 amps full load current, all the feeders in parallel, but each individual feeder only 300 amps. And you have to get a pickup. And this, you can see if using the RMD technique, as I mentioned earlier on, the load cutout, you can set the load cutout, but this load cutout will only cut out 3-phase faults, for example. That's the advantage of using the RMD technique, even in an application like this, compared to a classic distance protection. All right, this is what you can see here. For example, a face-to-face fault. We would see a face-to-face fault in here. The RMD can pick up, even though it is inside the load area of the impedance, the RMD technique will trip for that fault condition. And we want to go through all the calculations here, but it's just the principle to show you that you can get a good sensitivity and you can get tripping inside. You can set the load cutout that would apply to 3-phase conditions. It's a small limitation, but we don't typically would get 3-phase faults over here. 3-phase faults are normally if you're switching onto grounds and so on, but over here, remote faults with backup requirement is typically asymmetrical faults. The 3-phase fault, in the 3-phase fault, we would normally have a larger current and we would not be in that area. The 3-phase fault would be a bolted short circuit with a small resistance, which we would then cover inside the reach. Effectively, this single phase to ground faults, and so with the fault resistance, you see the problem, but that goes in this area, but those we can detect even if they are inside the load, because the load cutout only applies to 3-phase faults if you apply RMD. Okay, now we come to the more difficult situations here. Sorry, we're still with the face-to-face fault down here to showing you that the load cutout here will not be affected by that. The zone 2 can detect that fault inside the characteristic, because remember the RMD technique is detecting this would not pick up on a load here, but can detect on a fault because the substitute current is based on negative sequence, and during load we don't have negative sequence, so it will not pick up on the load condition, but the fault condition it will pick up inside the characteristic. That's why the RMD can trip for faults inside a load cutout if it's an asymmetrical fault. Right. One slide ahead now. Now I'm at the slide I thought I was at. Now we're at the transformer backup. This creates new difficulties for us, okay? Because we are now looking into a transformer, and this transformer, here we have a star delta transformer. It would also apply to a delta star transformer. Also star star transformers if they are not both grounded, but those are unusual. Y transformer with 2 grounds is unusual. If there's a delta in that, like you would have an auto transformer, the delta would also shunt the zero sequence to a large degree. The zero sequence would not come through that transformer at all. So we typically will see on power transformers that if you have a ground fault on the one side, the zero sequence will not be coupled through to the other side. And remember in our loop selection, that was an important requirement for loop selection, that we get a single phase loop can pick up only if we have a ground fault detection, for example. So normal distance protection is not always going to be ideal over here. In this diagram, we see just a little example here. And you can see at the bottom, the top is a circuit diagram. If you don't want to look at it in detail, you can see the L1 voltage at the top is over here. It's pointing down here. Look at the red arrow down to the fourth quadrant, or basically look at the angle. It's at, if you think of a watch, that's the center of your clock, then it's pointing to about 5 o'clock, right? And if you look at on the left-hand side, the star side, the HV side, the L1 voltage is at 12 o'clock or 0. This would be a YD5, okay? Because the Y is at 0. And on the delta side, the LV side, you can see the L1 voltage is at 5 o'clock, just for an example. But that's not important for us now. What's important is the bottom diagram. So the bottom diagram, you can see our relay located on the LV side, the delta side down here, is measuring this. And we have now applied a fault on the HV side. And we've applied a L1 to ground fault. And you can see the red phases show you the loop current flowing through that L1 to fault. There's current flowing out on the L1, through the fault and back in via ground. That is the loop on the HV side over there. And then due to the transformer coupling, that couples onto the delta side. And you can see there's current in this limb. So we will have current flowing out here on that phase, L1. And the current is flowing in here on L2, but it's not flowing, cannot flow through that limb because there's no current on the other side. Transformers must be balanced in ampere turns. The current is flowing on that bottom path up there similarly. So we get a phase-to-phase current here. It's clear we cannot get a single phase current on the delta side. It cannot just flow in. There's no star point return. So we see here we have a phase-to-phase current L31 during an L1 to ground fault on this transformer. So the loop that we need to measure with, the loop that we need to measure here is the L31 for L1 to ground fault on that side. And this would work in a classic distance protection, would be able to do this. So one, say some cases, the classic relay would see the voltage drop here in the loop L31, and it'll see the current in L1 and L3. So a normal distance protection could deal with this fault. It would work okay. Pick up there. Here you can see just the example, all the phases shown, the top, basically the UL1, and basically the voltage that side, the current this side. You can see pre-fault no load current, okay, pre-fault voltage, and then the faulted voltage here, and then the fault current, and then at the bottom you can see at the bottom the phase-to-phase current L31, on the HV side the single phase current. But this is, as we saw in the previous diagram, as expected, and you can see the voltage here, phase-to-phase voltage, sorry, there, phase-to-phase voltage, I should have probably drawn that, the L31 phase-to-phase voltage is the smallest one together with this loop current here would be okay for a classic distance protection. So you think, all right, that's very good and well, and that is going to work, and we would measure an impedance. I measured impedance I showed now in the bottom here, as one would expect a reverse fault, but remember in our relay settings, we defined the forward was into the 22 kV network and reverse was into the transformer. So the reverse zones into the transformer would pick up on this. So we can pick that up and it would measure 1.5 times the transformer reactance. That's something one must be careful of. The single phase fault on the star side is measured at 1.5 times the transformer reactance on the LV side. This is what you know, because there's some current disappearing into the zero sequence circulation here. That's the typical condition you will have. Nothing special there, but now we go on to the problem condition. What if the fault on the HV side is not a single phase ground fault, but a two-phase fault? Here in this example, L23 fault. Now in this L23 fault, you can see again the loop current flowing out here on L2 and in on L3, the two arrows on the HV side, and they couple then through the transformer to be a current here. And now we get a strange scenario. The current is flowing out here on the center limb. Okay, it's coming in from the top, but it doesn't flow through that winding. Obviously, there's nothing on that winding there, so the current flows here to the star and out, the one arrow. And the other one comes here, must match the current that we have on the other side, that flow in on this side to match that current through here. And so we've got two currents coming out here, one in, one in. No zero sequence. It's important. Even on the previous diagram, remember we had a phase-to-phase current on the LV side. Here we've got two in, one out, or two out, one in, and out here. So it's four, one going in, and two coming out. If you summate them, there's no zero sequence. No zero sequence current, no zero sequence voltage. And yet, we want to measure with a single phase loop. We want to measure with L2 ground. The correct loop to measure an impedance here is L2 to ground loop. A classic distance protection will not be able to do this, because a classic distance protection, to select the single phase loop, the L2 ground loop, it must have zero sequence. It must have ground current. So for this, that's why I said on the transformer, we should use the dedicated impedance protection. But impedance protection will be able to look into the transformer with the zone 3 and 4 and be able to choose the correct loop without having to see zero sequence current or voltage. Because the zero sequence current voltage is decoupled, removed by the power transformer. It is not coupled through. In the project tree, if you look in the project tree, you can see the distance protection. You can use distance protection classic or RMD, I would use, recommended here, the RMD technique, and set that for your zone 1, zone 2, which are looking into the medium voltage system. And for your zone 3 and 4, looking into a transformer, you can see down here, there's an impedance protection for transformers, which you can apply in parallel. And you can apply both in the same function group, the same line function group we applied there. And they would use obviously the same current and voltage, but it's two functions doing two different jobs. All right, that's showing step-to-step engineering. You apply the two functions, you get efficient result. You get also in your process data, you get information, impedance protection trip or distance protection trip. You know exactly what is going on everywhere. All right, that brings us really to, I think, our final topic that we want to talk about today, this morning, is teleprotection. The teleprotection is a very effective supplement or add-on to the distance protection. What can we see here? We can see here normal line, and as we saw this morning, the zone 1, typically 80%. That means you've got that safety margin over there, B, and a safety margin A from the other side. Both of those are about 20%. So if you look at the total line length, those two shaded areas sum up to 40%, almost half the line. So if you assume your line faults, really statistically, almost half the faults you will have will be either in A or in B, if your faults can be anywhere. That means half the faults you have on your line are not tripped instantaneously, because for the fault at B, we will have a zone 2 trip on the A side, and for the fault at A, in that shaded area, we will have a trip in zone 2 from the B side. It means the fault from either side, one of the sides will be delayed tripping, we can call it that. And delayed tripping is not good for power quality, system stability, and the many things. We want to try and avoid that, and the teleprotection will give us the technique to do that. Again, now in the Dixie project tree, you can see there are a number of teleprotection schemes. You can see the teleprotection scheme, distance protection is 25, 85, 21 are your distance protection teleprotection schemes. You get a blocking scheme, reverse interlocking scheme, permissive overreach, permissive underreach, 4 different schemes. The reverse interlocking scheme is added here. That's what we spoke about just now when we did the transform protection. Remember, for the LV bus bar, the 20 kV bus bar, the zone 1 with the reverse interlocking from the feeders. That's this scheme over here. It's applied as a teleprotection scheme because essentially you have the zone 1, which is controlled by the feeder with reverse interlock signal. So it's an external signal you couple into your distance protection. We call it teleprotection. Not going to be considered here. The schemes we consider here are for normal feeders, and for those we have the blocking, permissive overreach, permissive underreach. What you also see is 67N, the directional ground fault. Directional ground fault can also be applied with a directional scheme, and the combination of the directional ground and the distance protection can be very, very effective, especially we spoke about it this morning. Fault resistance, at some point, the fault resistance, if it's a high resistance fault, and that's why we sometimes refer to 67N as a high resistance fault protection or high ground fault resistance protection, then it goes beyond what the distance protection should be set to. Remember, we don't want to set the zone, the resistance reach of the distance zone too big. Remember, the symmetry requirements, X to R and so on, are limited. If you run into difficulties with the R to X of a distance protection, don't try and overstretch this. Say, okay, I accept the boundary for the distance protection, and I use the 67N to take over for the resistance. It is very, very effective for the high resistance ground faults, also with the teleprotection scheme. And at the bottom, weak in feed. Obviously, as I spoke about it in the renewables, for example, we said will typically be weak in feed. You get also other weak in feed conditions. And with the teleprotection, you combine a weak in feed logic, which will improve your tripping speed overall on both sides. So you can get, even at the weak in feed side, a fast fault clearance to remove the situation. I wonder, did I do 2 slides? No, it was just a... All right, the 4 schemes that we are typically looking at with distance protection: PUTT, permissive underreach transfer trip; POTT, permissive overreach transfer trip. Then we have a blocking scheme and the unblocking. The unblocking scheme, I want to initially already kind of take care of that. That is really not a blocking scheme. It is more a pot scheme, essentially, but it uses a special carrier situation that you have a monitoring channel on your communication system. It is a special way of using the communication system. That's why I want to leave that a little bit aside. The 3 schemes we're really looking at initially are the put, pot, and blocking. Starting with the blocking scheme. The blocking scheme, as you can see in the title here, talks about AM carrier. It is not restricted to that, but it's giving a little bit the background. Why do we use a blocking scheme, and what is a key situation where you could say the blocking scheme is important to me, I want to use it, and it depends on your communication. And the important thing is, if you use a blocking scheme, if you have an internal fault, remember that's the definition of blocking scheme. When the fault is internal and you want to trip, you are not requiring communication. That means if your communication system has difficulty to get the signal through a fault, remember sometimes the communication goes on the power line, like the power line carrier. So we can see the AM carrier referred to here. And you need to get the signal through. This signal might have difficulty getting through a faulted line. So if the line is healthy, then the blocking scheme would communicate, and you can be sure the signal will go through, because it's only sending a signal when the fault is external. And then the line is healthy, and the blocking signal can go through a healthy line and be received and blocked, and everything is stable. So the point is, the blocking scheme is essentially applied where you have got difficulty, or you cannot be sure that your communication system will work if the internal fault is there. Then you simply say, all right, I don't care if the fault is internal, I don't need a signal, so I'm going to trip. I only want to be stable on external faults, so I need a healthy line to send the blocking signal through a healthy line. That is a little bit the history there. The put is simple. There we use an underreaching zone to send the advantage. You can see at the top there, used for longer lines. Why not on short lines? Because definition of put scheme, you are using an underreaching zone. What is the underreaching zone? It's zone 1. Zone 1 is used to send. What is the problem with zone 1? On short lines, the X setting is small, and due to our X to R ratio, the R setting is also small. You don't get a secure resistance reach on short lines, not with the zone 1. Remember, there's a situation of tower fitting resistance, the weak in feed, and so on and so on. It's not very dependable on short lines. That's why you can see the put scheme is not good. Middle length lines, long lines, where you've got a fairly good zone 1 setting, you can have a good resistance reach. It's extremely simple because you only send when you have tripped. All right, so I've looked at these schemes, blocking and put, say that they come if you have certain external compromises. And in the middle, we've got the pot scheme. The pot scheme always works, okay? If you assume your carrier will get through a faulted line, obviously, that's why you can see using special frequency shift modern carriers. The AM carrier is an older type of carrier system, not used nowadays at all, I don't think anymore. Very cheap, well, not cheap, it's just older, all right? But the frequency shift carrier, you can be dependent that you will get through the fault. Also, if you couple the carrier onto two phases, gives you a better coupling of your carrier signal to the line. You'll get a dependable signal through the line, even if it's faulted. It will work on short lines. Why? Because you're using an overreaching zone to send. You will send also on external faults. And then you can see the problem is going to be you have going a more complex system because the receiving end will get a release signal even on external fault. It needs additional logic. And you get into transient reversal conditions where it can be complex. And so you need some additional logic, a more complex current reversal guard logic for the pot scheme. So that's really summarizing it. Put, extremely simple. Short lines is difficulty. Blocking, you get slightly slower tripping always, but it works even if your carrier system is very poor. Pot scheme works everywhere, but is more complicated. Okay, that's what one should just consider. So there's just a little logic diagram of this. I don't want to spend too much time on this. You can see here, this is the put scheme. Zone 1, your underreaching zone, is applied here. It's the one that's going to transmit the signal. And if you receive the signal over here, you would simply use an overreach. You release an overreaching zone to trip immediately. Basically, it's just simply very, very simple. You could almost take the received signal and trip directly. You don't do this because there is always a risk of a mistake by the communication. If the communication sends you an unwanted command, so just by accident, and there are some probabilities statistically, I don't know whether 10 to the minus 4 or 5 is the probability. So if you've got 10,000 power line carrier systems, you'll get about one unwanted command per year or something like that. If it then directly trips, that would not be good, even if it's only happening once a year. So you put that received signal into a zone 1 overreaching zone release, and that means that the chances of that unwanted command coming from one of your 10,000 relays once per year and a zone overreaching zone pickup at the same time, that is not 6. That's if you're going to win the lottery 3 weeks in a row, effectively. All right, the pot scheme looked almost the same, only is that we are now using an overreaching zone to send, right? And you can see with the received signal, the release is the same. Again, the received signal would release your directional overreaching zone. So it is like a direction comparison. If you have an internal fault, then both sides, zone 1B will pick up. The one side sends, the other side sends. They're both sending, both receiving, and they have a pickup forward. It's a trip. If the fault is reverse, over here, the remote sides would see it in zone 1B would send. The local side would not see it in its forward zone, would not trip, okay? But the local side would not send, it's reverse. So only one side sends here, and the receiving side will not see the fault in its zone 1B and no trip. So the system is stable also. It's a direction comparison scheme effect, not exactly, but almost. Blocking scheme is a little bit different. Here you can see there's some logic over here. Pick up forward would block it. You can see, be careful here. See, pick up forward, but it goes in inverting input, so it's going to block the send. So you have a pickup wants to send, but if it's a forward pickup, you will not send through the AND gate. It's blocked. So you will only send any pickup, so very sensitive, but not forward. So every reverse fault you see, you will send a blocking signal. And on the remote side, when you receive the blocking signal over here, you're going to go in and prevent the tripping. So sorry, here you see the receive signal comes here, inverts the input to the AND gate, and the AND gate is blocked. You cannot trip. You need some time. Now, the problem is when you get the pickup and you immediately want to trip, that would be too soon. You have to wait for the receive signal. And that's where you have this coordination time here. You're waiting. That's the T. You're waiting. It's the channel delay time, safety margin to wait for to give the remote side to send you the block signal. If you don't have the block signal when this timer here expires, the permissive scheme will trip. And then you see at the top here an add-on which is not classic blocking scheme. It's an option you can apply together with a blocking scheme called so-called jump blocking. The jump blocking will send immediately at fault inception. That is extremely fast, about maybe 15 milliseconds faster than normal pickup. So it comes on a sampled value immediately. It does not have to filter out anything. It comes on the delta at the fault inception. You can see the delta. So it's approximately 15 milliseconds faster than the pickup here. That can send immediately, but it's not directional. It's just saying send immediately. And then that way you would get the receive here very quickly. You get the receive if the channel delay is 15 milliseconds, you get the receive here at the same time as the pickup. That means you could, in theory, change this time TV to 0, approximately. Because your jump blocking will be here when you get the pickup. Normally you can reduce the time. I wouldn't necessarily set it to 0, depending on how fast your channel is, but you can reduce it. And the technique is like this, that if the fault is reversed, then this blocking here would be taken over by this blocking, and the blocking signal continues and you won't trip. If the fault, however, is forward, the forward detection, you can see here, will reset the jump. Immediately, as soon as you see forward, you take away the jump block send. That means that the other side, the receive signal, will be taken off. And as soon as the receive signal drops out, you can then trip. So it is just an add-on to make it possible to set this timer a little bit shorter. You don't need it, but can be used. The unblocking scheme, remember, it's the final one I said, is not a blocking scheme. It's an unblocking scheme. It is actually a permissive overreach scheme, but it uses 2 carriers. You can see it's FU and F0. The F0 is a monitoring signal which is sent all the time. It's written as F0 and FU because it's typically done with a frequency shift carrier. It means you've got your 0. F0 is a frequency which is your monitoring or blocking frequency. As long as you receive F0, the received block is happy, says the channel is healthy, is ready. If the F0 disappears, it's going to say, "Ooh, okay." It could be a fault. It'll have a certain time. If the unblocked receiver is then received, then it'll say, "Okay, I have dropped out F0, I've picked up FU, I will release, and can release the tripping," essentially like a pot scheme. If, however, the F0 disappears and FU does not come, then there's a certain timer here, and timer will say, "Oops, somehow the carrier has failed, the communication has gone away. The F0 has disappeared, I'm receiving nothing, I'm not receiving FU or F0, channel failure." It'll give you a channel failure alarm, and the logic will deal with the communication failure. That's just a different technique of doing it. That is different received block as such. The teleprotection can be phase segregated. This is a big advantage in some applications. It's sometimes also forgotten. Here we see a double circuit line. And we did have the question this morning about the 4 lines on one tower and so on. And we said, obviously, the mutual coupling and so on is very, very difficult to consider there. We have to set a smaller zone 1. And in these applications, double circuit lines, your dependency on the teleprotection is higher, right, to get security, because you would probably have to set your zone 1 smaller to make allowance for the influence of parallel line coupling. So the teleprotection is extremely important here. And the other thing that can happen on these double circuit or multi-circuit lines, you get inter-system faults. Okay, and for this example we've shown, it's the same voltage potential. Maybe they were actually coupled on both sides as well. And you get a fault, A ground on the one tower and B ground on the other tower. It's probably maybe an inter-system fault that they are flashing over to the tower, and the arc on the tower burns into the other line. So you get this. Normally, if these were 2 independent lines, not on the same tower, the chances of a fault A ground, B ground happening simultaneously is very, very small, very remote. But if it's the same tower, meaning it's 2 circuits on one tower, then this type of fault is not so remote, can happen. And we want to get phase selective single pole tripping on both feeders, because if we trip both feeders 3-pole, that would be really, really a bad interruption of the system, because we would maybe lose complete interconnection of the 2 stations. If we get a single pole trip on both feeders, then the 2 stations are still strongly connected. You can get a lot of power transfer between the 2 stations. They will remain synchronous. The stability is much, much improved. All right, how can one do this? You can see on this side, if it's all coupled on both sides, then there'll be a pickup here, zone 2, AB ground. These two relays would pick up face-to-face to ground and would want to trip 3-pole inside the zone 2 because it's a remote fault, all right? These two sides would see A ground and B ground single phase forward, zone 1 trip, and then if you use a teleprotection, either put could be used here because the zone 1 pickup, or also a pot as such. These remote sides would send a phase segregated signal, not send, they'd send us, say this one would send a B release and he would send an A release, and on the receiving side, they would say, although I have a pickup AB ground, I only get a release for A, so I would trip single phase. So you can get single pole tripping at both sides for this condition here. And that's, as I say, done in the logic independently. You can do this with binary inputs or, as we'll see later on, with the built-in serial communication. So you have a choice. You can do this phase selective tripping with binary inputs or with a protection interface. A protection interface is the serial interface in the relay. This could also be an Ethernet interface nowadays. For a couple, well, it's almost more than a year now already. You have the BD module. You can put the like the protection interface over IP. Use a BD Ethernet module to get the communication. But that's a different subject. Okay, so the way in which your protection interface is configured doesn't really matter. That's an internal serial or IP interface to the remote end, and you can put your signals through this interface, or you can put the signals through contacts and binary inputs in the classic sense. Both of those can be phase selective, as you can see here. The binary inputs there, you can see there's receive ABC. You define each one independently. And further up, there would be send signals also individually, ABC send, which you can route independently. If you use a PI, it will automatically be phase selective. So in the PI protection interface, you don't have to set anything special to be phase selective. It is automatically phase selective, the PI interface. Transient blocking, all right, that's a nice subject here, which one can talk about for a while. It is important for the permissive overreach scheme, all right? In the permissive overreach scheme, remember we said we have the condition that we will be sending on the external fault. So here I've taken an example. At the top, for example, you can see here 2 feeders again. Does not have to be a double circuit here, but here again, on the double circuit, this is amplified, or this problem is more probable because of the mutual coupling, what we spoke about earlier on, that during the second condition here at the bottom, the mutual coupling will pull this fault closer to the relay location, but that's just something else one can talk about, a bit technical. But on a simple level, the transient blocking is important that the relay here remains stable, the top feeder remains stable and does not trip during this reverse fault, even though this reverse fault for the top feeder is going to be cleared sequentially. That breaker remains in while this one trips. Let's go through it step by step. So initially, we have the top condition and we apply the fault here. Then I think there are some diagrams. No, they won't. I have to go through it one by one. Sorry. So what happens here initially, we will have a pickup on the right-hand side reverse. And on the other side, we'll have the zone 2B ground. So the left-hand side at the top will be sending a signal. Here we will be receiving the signal, right? And this side at the bottom, we'll see the fault here outside zone 1, but inside zone 1. So maybe the teleprotection is not working so quickly. And then we go over to this condition trip. And now things reverse. So you get a reversal here that now over here, the zone 2 is going to reset, stop sending. Over here, you could get a zone 2 pickup and send. Now you can say, all right, why should this zone 2 pick up for the fault all the way down here? It's, as I said, sometimes you can consider the mutual coupling, but if you've got the fault current flowing in opposite directions, the zero sequence current, the mutual coupling will pull the fault closer, okay? And it could be that you've got a larger zone 2 setting to make allowance for other difficulties you have. So it's not impossible that the zone 2 will pick up once this breaker opens here. Now remember, from the top here, this side was sending a signal, and when this reset happens, it will stop sending, but this is a channel turnaround delay. the receive signal could still be present when we change to zone 2 pickup here. And remember, zone 2 pickup and receive would be trip. We would trip this breaker on that condition. For that purpose, you need the transient blocking. And the transient blocking is really very, very simple. It's this relay over here, which will activate it. It'll see the reverse fault. You have a setting over here. The first timer, the block pickup delay, that timer there, the 105 timer, and the number of it. You can see there, if you have a pickup that is not forward, or a pickup that is backup, that's an OR gate as such, and you have a general distance pickup at the bottom, those 3 inputs you see over there on the logic. Distance pickup not forward, distance pickup backward, or distance pickup backup, and a distance pickup. Those 3 conditions give you the input to the timer. And if the time delay is exceeded, then you would expect that must be a reverse fault. And the time delay you set on the pickup delay is the typical breaker time here. So you're saying, I'm seeing a reverse fault. I'm expecting this breaker here at the bottom to trip. So I'm just going to wait the time of the breaker. And then I'm saying, if I've seen it for that duration, typically about 20 milliseconds, then I will be sure that there's definitely a reverse fault, not something transient. And I will activate the transient blocking. If now this breaker really does trip, then the transient blocking is active and it will not drop out instantaneously. You have a block hold delay, which is typically set to around about the channel delay times 2, typically about 50 milliseconds you set here. So for a further 50 milliseconds, you'll keep the transient blocking active. And that means even though you have a zone 2 pickup now, and you may still have a receive which has not yet reset, you will not trip with the pot scheme because the transient blocking prevents it. And you will also not send a signal. That's the other interesting. You will also not send a signal. Normally, the zone 2 pickup will send a signal, but the zone 2 pickup with the active transient blocking, there will be no send signal. It's really sounds more complicated than it is. It's really fairly straightforward. One other aspect we still need to look at quickly is the weak-in feed. The weak-in feed really is 2 aspects. The one is the echo and the other one is the trip. The echo is clear that if you have a weak-in feed condition, you want to tell the strong-in feed, look, I'm not seeing the fault, but it's definitely not reverse or anything, so I'm going to send you an echo and you can trip. The weak-in feed tripping is, again, more secure, again, because of remember the unwanted command. If for some reason the remote side sends a signal and there's not really any fault or anything, it is just an unwanted command that the communication equipment did by mistake. We don't want to trip on that. We will check the voltage criteria. You can see there's an undervoltage check. So if that unwanted command is received and you have an undervoltage, then in theory you could trip with weak-in feed, but that should normally not happen. Normally, if the system is healthy, you will not have an undervoltage. All right, I think there are small logic diagram for that. I think that's from the manual. I don't want to go through this in too much detail, but you can see at the top, there's basically going to be an echo release over here, which is coming from the distance protection and weak-in feed. There's a certain logic saying you must have a distance protection there. If the distance protection is switched off or the settings, there is no distance protection, you cannot get an echo release. So if the distance protection is blocked due to emergency mode and you have an emergency mode, then the emergency mode can replace the distance protection. So that's done internally. You don't have to, there's no settings required for that. It's done in the internal logic. If, however, you get basically a weak-in feed condition, but you have a receive signal and everything is healthy, and there is no pickup, then you would say, all right, I'm getting a receive signal, I have no pickup. So for me, it looks like I'm a weak-in feed because you are receiving, and you would then release the echo, and the echo would then be sent here. There are some stabilizing techniques here to prevent ping-pong echoes, that the system locks itself up, that the one receives an echo and then you send it back. There's this timer which says if I have sent a signal, I cannot send an echo shortly afterwards, otherwise you get the system locking up. That's all done internally with the default timers. So essentially, if you have the no pickup and receive, you can see that on the left-hand side there, there's a receive for echo going in there, then there's no pickup. Listen or emergency protection, no pickup, then that'll release the echo. The echo release, if the timing here says there was no send signal, I didn't send a signal, so I'm not echoing my echo, and so on, then it will release an echo signal out here to allow the tripping. The thing that we must worry about if we're going to apply the pot together with some weak-in feed is that our zones are set correctly. And we must have a reverse reach. And this is a standard teleprotection scheme, whether you're talking about blocking schemes or weak-in feed schemes or echo schemes. You must have the reverse reach, which covers the remote forward reach. And you can see this green area is correct, because the local relay here has got a reverse reach that goes up to here, this point here. And that reverse reach here is larger than the remote side forward reach. The remote side forward reach only goes up to here, and the reverse reach for this side goes up to here. So you have a good coordination. That is correct. On the other side, it's incorrect, because you can see the reverse reach of the A is too small. The B side at the bottom here, this B side reaches all the way, you can see, to the complete left of the pickup. There is this pickup B4 on the remote left-hand side. It goes further than the A side reverse reach. That's why that red area is not big enough. That red area, the reverse reach must exceed the remote forward reach. And it's important, because if you receive a signal, then you must, and it's a reverse fault, then you must see at least the same distance reverse as the remote side sees forward. All right, that concludes our presentation this morning. I'm looking forward to lots of questions.
Yes, a lot of questions we have, even from the beginning. There is a question related with the latest topic.
Okay.
And is the first one, or the second one that we got, is difficulties to implement the airfall carrier in CProtect 4 device during line airfall distance and airfall both operate in CProtect 4, for example, in 7SS52 or 7SS61. I need this question answered very much. Here is saying, because FCON airfall is very important. Is FCON very important in all the lines, or in some cases it can be omitted? From your explanation, I think we need it. But
it should be, it's a big advantage, as I said, because the fault resistance, if you can be sure that your fault resistance is always very small, then you can ignore it. But if you've got high resistance fault, and they can always happen, then the earth fault should be applied and is a very, very strong supplement or extension of the distance protection.
Yes. There is another question now from AC. Teleprotection signals between two ends have been transferred via the direct fiber optic connection and separately via third-party multiplexer equipment. That is the traditional scheme, no? To redundant protection schemes. Will the 8521 and 8567N function short work in situation of direct relay-to-relay communication failure situations as well?
Yeah, obviously, I mean, if you're using a protection interface for your communication, and we recommend to do that because it's phase selective and fast. If there's a failure of the communication, then obviously the teleprotection scheme will not trip, but it will not maloperate. So that is, you have to accept that. Obviously, if the communication is not working, the teleprotection will remain stable.
Yes. That's important also to have two redundant channels, for example, in high voltage lines. No? From VV, this is related with the application that you show about the transformer protection. Zone 3 and Zone 4, transformer backup. Example, there is a fault, phase 1 to earth on high voltage side. The issue here is that the protection relay installed in medium voltage side see face to ground fault on high voltage side as face to face only. If CT are located outside of the transformer delta, is there any issue if CT are located inside the transformer bank?
Right, we have to be careful that the CT locations are used here were the classic ones, which are obviously on the phase conductors on the both sides. So we're only looking at the low voltage side. If you have a delta winding, obviously you sometimes can have CTs inside the delta. That is a different situation, because then you have to reconsider, because there you will see the face-to-face current effectively as it would be on the outside. One would have to set it differently, but you would not normally apply that, because it depends. If it's an isolated system, you could probably do that, but we'd have to look at it separately. But that is not a normal location for CTs for the feeder protection. So for transformers inside the transformer, in other words, on the delta legs, it was inside the transformer tank, and essentially those CTs we would have to consider separately. It was not done in that application note.
Okay. There are some questions related with the first presentation, and for example, if we can apply the reactance method for all the lines, for all the cables, and for phase to ground faults.
Yeah, the reactance method is basically our preference. I think it's maybe newer to us. It's only new, it's not so new, but it's other than the classic, it has got the advantage of the load compensation, which is something which we did not effectively have with the SuperTech 4. That's why, and I would recommend to use it because it's also a default, and there's no reason not to use it. You can use it on all cables and feeders, and it has no disadvantage to the classic, except that you have 1 or 2 settings additional that you have to consider.
Yes, okay, thanks. Here there is another one that we have also in the chat. Could you please elaborate consideration of source impedance for the distance relay installed at the start of the line at generation power station to station?
The source impedance is not really part of the distance relay setting. The source impedance would be considered obviously in your CT dimensioning as such. If you, I think that what you're doing source impedance at the generating line, it is not really relevant. The source impedance will only affect the magnitude of the fault current. What you need to check is sometimes the source, basically the SIR, the source to line impedance ratio, the SIR, source to source line impedance ratio. That can be an aspect in terms of the line length. If you have an extremely short line, you get to a source impedance ratio which exceeds maybe 50 or so, then it could be critical that your zone 1 setting is not going to be working anymore. But that would mean the line is too short. That's the only time where you really have to look at the source impedance ratio, but that's a topic which maybe one can look at separately. There is there are only some slides on that, but it's an interesting topic. But typically you would find a source impedance ratio, as long as it's bigger than smaller than 50, you can apply the zone 1 without problem. If your source impedance ratio is larger than 50, extremely short line, then you should check your zone 1 setting. It could be a problem.
Yes, there is also a question in the here related with the length of the line. If we can apply the distance protection for lines shorter than 4 kilometers, for example, then I think this clarification is important.
I'll remember that for the next sprint, the second top session we will have in a couple of weeks. I'll bring that in the short line and the source impedance ratio. It's a good point.
Okay. Here, I think it's the last one. We have a lot of, but we are we have running out of time. Is distance protection? This is related with the weak in feed. Is distance protection necessary for a high voltage consumer without generation, radially connected to the high voltage bus via transmission line or underground cable? Some TSOs require distance protection and line differential together, and ask for distance protection relays at consumer side and bus side. How to configure the relay at the consumer side in this case? What will be the forward direction for a consumer without generation?
This is a classic situation where you have to check if you are going to be a fixed weak in feed. Now, it can be, I think also with the renewables, we saw that the in-feeds are changing. But if you are basically on only a consumer side, you can still apply a distance relay so that you can get the teleprotection scheme. But if you are not going to have any teleprotection, then applying a distance relay on a pure consumer side becomes less functionality. But you have to remember that even if you're a consumer side, if you have a grounded transformer, for example, behind you, you will get zero sequence in feed, and the distance relay can perform even if it only has zero sequence in feed, can give selective tripping. There's also, as we spoke about, direction criteria for the pure zero sequence in feed. The distance relay has got a special detection for that and would give a correct directional decision. It's a so-called Bauch paradox, is where you get that we have no in-feed from any positive or negative sequence, but only zero sequence. The distance relay will detect that and can give proper direction and loop selection.
Okay, that's good. Here we have also a question in Spanish, then I cannot leave it. how the distance protections works or interact with the auto reclose, but I think in the next session we are going to explain that.
Yeah, the auto reclose is a very, very strong supplement for feeder protection or line protection, I should say. And we have got a really, really nice auto reclose function and works well with distance protection.
Okay, dear auditorium, thanks a lot for your questions. And also thanks to Gustav for the quite interesting presentation. I still learn a lot also. Every time that I'm here, I learn new things. That's good.
That's good.
Also, thanks a lot to the auditorium for the questions, really interesting questions. And the questions that we are still open, there are a lot. We will answer later on. We will contact, and we will get back to you soon. Also, the access to the recording is automatically available to all participants directly after this session. And then, thanks a lot for staying with us. I'm looking forward to see you in one of the next sections. That is the distance protection applications, April 20, 9 to 11. Then see you there. Take care and goodbye.
All right.